new ideas to impact the world in terms of energy, concentrating on the renewable energy. The experience so far is very good. It's the third day, but I think I've gained more knowledge than I expected. Right now we are doing the hands-on, it's the practical unit, and I think they're impacting very well because it's easier to understand when it comes to the practical sessions more than the theoretic. And I think it is very beneficial to me so far.
The experience is good so far. At the end of this program, I expect to have gained more knowledge, to be able to understand how to install appliances, how to choose the correct appliances, how to deal with customers and their demands. The experience has been very inspiring, being that there are more female students than male students. It's actually a great honor. So, yeah, the program so far has been good.
It has been a wonderful experience as an intern here. I've been an intern for the past 1 year since the consortium was established, and it has been a continual educational and a learning process. When I see myself wearing an overall, when I see myself carrying a solar panel, when I see myself connecting a battery to power the loads, it has been a wonderful experience being part of the consortium. And next to it, we are proud and even more happy to have the first T1, T2 training.
But there's a guy there is so-called Robinson.
Yeah, that's Robbie, right, that's his name.
Robbie, a lifetime emotional support.
It's in the website.
That's very good.
Well, the students love him, right? So
I hope there's a person that is there. I don't know. Because there was that picture there.
Yeah, he's part of the team, so.
So, Patani works on she works on femtosecond lasers, where she is illuminating molecules and then measuring what is transmitted, right? And before she joined Max Planck Institute for the Science of Light in Erlangen, Patani was in Max Planck Institute for Quantum Optics in Munich, where she also did her PhD under Professor Krauss. Now, Professor Krauss is the Nobel Prize winner. So the person who is talking to us has been mentored by the 2023 Nobel Prize winner. And even to make matters better, now Dr. Mataki is working with Professor Gerd Roix, and today we are honored to have Professor Gerd Roix in the house. Probably Professor Roix, you can just wave at the crowd. Hello. Now, Professor Roix was my PhD supervisor some years ago, and he is a very inspirational person. Oh, thank you. Hello? He is a very inspirational person when it comes to science, and a person with a lot of information. You can sit down with him for many hours and you are not going to get tired. Now, tomorrow we are going to have the honor to have him give us a lecture in the morning. Please make sure that you are here, the first lecture in the morning. And of course, you can tell also your friends. I think this will be also quite important. Of course, all the lectures are quite important as well. But I think that will be a great honor. So, Dr. Fatahi is going to give to us the lecture on the solar pump tracers. We are really looking forward for this. Of course, all of us know about the solar. But now how can we pump a solar material using, how can we pump the laser material using solar? So I think we are interested in this and we are looking forward for this. Let us welcome Dr. Hani Fatahi to give us the first lecture this morning.
So, okay, it's on. Thank you very much, Geoffrey. So they say that mentors are so important in science. The PhD supervisor for sure is one of the mentors. And I can easily say that my second mentor has been Gerd Roix, who is sitting here, and he really influenced my life. So now I start from where we left yesterday, right? I just review a little bit very fast what we talked about. And then I just close this discussion on attosecond pulses and ultra-short pulse spectroscopy, and then we move on to the solar lasers, right? Which is one of my favorite topics at the moment also. Where is my pointers here? Okay, so we started with this graph, right? We looked at the history of the developments of the laser. We said that the first laser was invented in 1960. The first solar laser was already operational in 1963. And then there were some very important moments in the history. For example, one of them was the Kerr-Lenz mode locking that really led us to generate very short pulses below 10 femtosecond. The other one was the chair pulse amplification, which changed this plateau, that people could not increase the focus intensity of the pulses anymore, and chair pulse amplification changed the history. And that's why the inventor of it got the Nobel Prize, Gerard Mourou and Donald Strickland. So the other, the chair pulse amplification also enabled the generation of attosecond pulses, which we talk a little bit about them today. Then we talked about the ytterbium-YAG thin disk lasers, which led us to have very high energy pulses, very high power pulses. but at 1 picosecond, so they are not very short. Then I thought it's good if you see this one. For example, one of the recent applications of these very high energy pulses is for laser-guided lightning. This is the experiment which was performed in Switzerland on top of a mountain. And you can see this green light which shoots to the sky. So this is the laser, and it has so much energy, and it's focused, and it has so much intensity that it creates a channel in the atmosphere. So it ionizes the molecules and atoms in the atmosphere. Why they did that? Because when you have lightning, then the lightning hits the objects on the ground, and it can cause damages, right? So then the idea is that by lasers, you create a plasma channel that you can trap the lightning and avoid damage on the ground. So I thought it might be interesting for you to have a look at this paper, which was done by Ytterbium YAG team disk lasers. So then we talked about short laser pulses, very short, right, sub-10 femtosecond. And then we said that this regime, a new parameter is important, and that's called carrier to envelope phase stability. So we talked about the fact that if you want to generate a short pulse, you need a very broadband spectrum. And in the normal case, the pulses that come out of the laser, pulse to pulse, you have a different carrier to envelope phase, right? It's changing. So then there were 3 scientists, Professor Ted Hensch, Hall, and Glaube, who came with a technique to stabilize the carrier to envelope phase. Yeah? So shot to shot, you have identical pulses. So this was a very important technology. From one hand, it's so important for the generation of attosecond pulses. From the other hand, it opened a whole direction of frequency comp, that now you have a ruler to do very sensitive measurement. Okay, then we talked about pulse synthesis, how to make really, really short pulses. And then we talked about the fact that you can generate these short pulses and then synthesize them in the time domain and get optical attosecond pulses. So, can we start? All right. Okay. Then we finished the lecture yesterday by this picture that why do you need to be fast? Why do you need femtosecond pulses? Why do you need attosecond pulses? Why you might want zeptosecond pulses, right? You can even go shorter and shorter. There is somehow no limit. So for that, then, okay. I would like to motivate you that why ultra-short pulses are needed. Okay, let's start with a very simple experiment. Imagine that you are sitting under a tree and an apple falls on your head, right? Then there is a person in front of you. Let's say this is Newton. He's about to discover the gravity. And then there is a person who tries to capture this very important historical moment. Then he has a camera. The camera has a shutter, right? And if the shutter of the camera is not fast enough, the picture that you get from a moving object is going to be blurred, right? So you cannot see the apple falling off. Then the photographer is very unhappy. Then he dreams about doing such an image, right? But his technology is not good enough, right? The shutter of the camera doesn't close and open so fast, so he just blurs all the pictures. This was the thing that people worked on it a lot in the history, right? So in 1878, so now I'm talking now about ultra-fast technology of 1878, a gentleman who is called Stanford and who is the founder of the Stanford University, he had a question. He had a love for horses, and then he was really annoyed by the way that the paintings draw horses, right? Painted horses. You see, it's like, it looks a bit weird, right? The horse is very much stretched. And then he was thinking that this is wrong. I mean, the horses don't look like that. So we have to take a picture of a horse when it's running or galloping, that we see how it works. Is it possible that all four legs are up in the air? I mean, does the horse runs like this? But there was no fast camera to take a picture of horses. Then he met this gentleman, Edward Muybridge. He was a photographer who was just wandering around in the US, and then they talked to each other, they bet, and then he said, I can take such a photo for you. To do this picture, then Muybridge put 24 cameras over 36 meters, right? Simply because there was no fast camera at that time. And then he had strings attached to the shutter of each camera. And then he pushed horses to walk over this distance. So the horse walks. Now, he doesn't want to walk, okay. And the shutters are released, right? Then he takes picture, 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 picture. And they put the pictures together. This is the first animation that was captured with the very high speed, right? And you can see that the horse has 4 legs, four hoofs up in the air, but they are not in this way. They are towards his stomach. So this is the ultra-fast technology of 1878. Then the next breakthrough is about 50 years later, and that's in 1930 by a scientist who is called Harold Egerton. He was at the MIT, and at that time, people had xenon flash lamps. So you see that if there is an invention or development, you need some other fields to also move on, right, that you can take advantage. So the xenon flash lamps had the opportunity that they could just turn on and off in microsecond time scale, right? Every microsecond there was a flash of light, okay? Then he used these flash lamps to take pictures of an apple, for example, right? So the apple was there, the flash lamp, and then the camera was behind, and the flash lamp was just shining. He started to take pictures of moving objects. And that was the first time that people could just get these beautiful images, right, of a bullet going through an apple, because now the camera is fast, right? The flashes of light which turn on and off are very fast, microsecond. They could take an image of a person who plays golf, and so on. So this technique is called stroboscope. And it's somehow the root of all femtosecond and attosecond spectroscopy or imaging that we want to talk about today. Okay, what about the fact that you want to look at faster things and smaller objects, right? So this is the water molecule, right? This is H2O. And they vibrate, if I can activate it again, which I can't. Oh my God, okay. So see, they vibrate very fast. And if you just measure, then you see their vibration is at the femtosecond time scale. It's like 10 to the minus 15. But we don't have any light that turns on and off like femtosecond, right? So we need something like the stroboscope to just turn on and off that fast. So that happened in 1980, so it's 30 years later after the stroboscope. And the technique is in principle called pump-probe spectroscopy. And it was demonstrated by Ahmed Suwail, and he got the Nobel Prize for that in 2000. So how the technique works, now you see that why femtosecond lasers are important. You have a femtosecond laser, then you generate 2 beams from this femtosecond laser, which is called pump and probe. Then you put your sample here. With the pump beam, you pump your medium, right? You excite the molecules or whatever you have. At the resonance, you push them to move, right? And then you move the probe at different time delay towards the pump, right? And then you just, with the detector, measure what you see, right? This is called pump-probe spectroscopy. And what you get is such a curve, right? So when the pump and probe are together, and then afterwards, after the action, then you just start to see these modulations, which are in principle the response of the molecules. So this was the first time that this measurement was done. And it's called, we changed the chemistry because the chemist could understand how the molecules react and what happens at very fast time scales. So this is where we left yesterday. What about looking at even faster phenomena, even smaller things, and even deeper things, right? What about looking at the dynamics of the electrons? So if you look at how fast the electrons move, then they move at the attosecond time scale. This is 10 to the minus 18. Then you need a flash that turns on and off at attosecond, right? So that's why the attosecond pulses are so important. But then we talked about it, right? There is no laser there's no material that you can put in a laser and have an attosecond laser, right? Because light gets absorbed in matter below 150 nanometer, and you need shorter wavelengths, right? So then at the same time, people were frustrated that they couldn't have very short wavelengths lasers, but there was chair pulse amplification, so they had very strong lasers. And they thought what to do. Then they started to focus these very intense pulses to the gas. So this is a gas nozzle, and then you see that the light is focused to the gas. They started to focus the light to the gas. When the intensity was low, you are below 10 to the 13 watt per centimeter square. You are at the ponderomotive regime. This is the regime that we talked about it yesterday, that you see second harmonic, third harmonic generation, and so on. Then they saw, okay, they start to see different harmonics, like third harmonics, fifth harmonics, seventh harmonics. So you only have odd harmonics because gas is a symmetric medium. And everything scales very well, right? So, and then you have multiphoton absorption, for example. You can have n number of photons with lower energy than your band gap, and then excite the electrons and ionize the atom and so on. The physics worked, right? But the lasers were very, okay. So the lasers were very strong, right, at that point of the time. And they could deliver intensities at this scale, 10 to the 14 watt per centimeter squared, right? So this is like a terawatt scale intensities. To give you some ideas how intense the light is, now if you just gather all the sunlight which falls on the Sahara Desert in Africa and focus it into a postage stamp this size, this is the intensity that you get, right? And this is the intensity that you need to do all this attosecond dizziness. So lasers with the chair pulse amplification had that intensity. Then they started to focus the laser to the gas again with a high intensity. And then they saw a completely different behavior. They saw that many harmonics, so I was thinking it's me, so it's you, so, It's okay. So they could see that many harmonics are generated. And it goes beyond, you are at not second, third, fourth, seventh. We are at 30s, 70s harmonics, right? So it's like that the reaction is completely different. And then the amplitude doesn't drop. You see, it's just that it's like you have a plateau and then a sudden drop. In the other case, they were all going down slowly. So it has this kind of behavior, right? At lower intensity, the harmonics just go down. Then when you have very high intensity, you get a plateau of very high harmonics, high order harmonics, and then you get a cutoff. This process is called high order harmonic generation. And it was very important, right? This was the non-Pandermotiv regime. That's when the nonlinear optic that I put in yesterday on the slides didn't have any meaning anymore. And there were so many work on this part, which was done by Anne-Louier, who is one of the Nobel Prize winner of 2023. Okay, so people were scratching their head, and they just didn't know how to describe this process until, so this slide comes afterwards maybe. Until a scientist who is a, okay, oh, too much, okay. Okay, there is a problem, but I just try to explain it. Until a scientist who is called Paul Corcombe came with a theory about how this process is happening. So, how he explained it, he said that you have few cycles of light, right? Then the light come and interact with your atoms. Then you bend the potential of the atoms, right? Because it's so strong. Part of the electrons just tunnels out. Right? And then the next oscillation of the light comes and brings back this part of the electron, which is electron cloud, which is tunneled out, bring it back, smash it to the atom, and then generates light. So because the field is so strong, the force is so strong, right? You bend the potential of the atom, the electron tunnels out, then it gets accelerated, and then changes the direction, comes back to the atom, and generates XUV pulses. This is called a three-step model, and it has a very simple mathematic. So I would go and look at this paper. So it's really like F equal ma type of mathematics. You will understand it. Okay, but then we just talked, right, that you have like 2 or 3 cycles of oscillations of the electric field under your envelope, right? Then at each of these cycles, you generate a burst of attosecond pulses. That's why they come in a pulse train, right? It's not isolated. I mean, there will be a lecture next week about generation of isolated attosecond pulses. I just go through it very fast. This was done by Ferenc Krauss, the measurement of the isolated attosecond pulses. And what they figured out with Paul Corcombe was that the cutoff part of the harmonic generation, you see it's not modulated also, right? This part should correspond to isolated attosecond pulses. Why was that? Because that part, the cutoff, has the highest energy, and it comes only from one peak, right? Because you need the strongest part of the field to generate that. And then what they did, they simply put a filter. They just filtered out this part, which is isolated, and then they had the isolated attosecond pulses. And that brought these two gentlemen and Anne-Louier the Nobel Prize of 2023. Okay. So, how short are attosecond pulses? I mean, there was this discussion yesterday about the efficiency. The process is not efficient, so you don't have so many photons, right? But let's say that to have enough sufficient photons to do some measurements, at the moment you can generate 53 attosecond pulses, right? Or 300 electron volt photons. And you can do so many physics. I think this is done in the University of Florida. And you can do beautiful science with that. Okay. So let's say that how the whole thing scales, how you can generate shorter pulses and how this, everything scales in the attosecond business, let's say. So it's all about this very simple formula here, right? So that shows, this shows your cutoff, right? Your cutoff frequency, or the highest frequency that you can get. It scales with the intensity of your laser, so the more intense, the better. Then it scales inversely with the frequency of your light, right? The laser that you use for this process. So if you use a longer wavelength laser, you get a higher cutoff or shorter attosecond pulses. But the problem is that you cannot really increase peak intensity indefinitely, right? Because then you excite all the electrons, ionize them, and then there is nothing left for you to do attosecond pulses. So then there is a parameter which is called Keldysh parameter. It's good that you hear the name of Keldysh also, that defines, right, the regime, that what should be the intensity to see attosecond pulse generation. Okay, now you have this very short pulse. Don't have any camera that has a shutter with attosecond pulse, attosecond speed, right? So you need a technique to be able to measure it. So what Ferenc and Paul Corcom did, they did attosecond streaking to measure these attosecond pulses. So the idea was from Paul Corcom, and Ferenc showed it experimentally how it works. In principle, they were inspired by the way that the attosecond pulses are generated, right? They say, okay, so we have the laser pulse, and here you can see the XUV pulses, the attosecond pulses which are generated and propagate together with your laser pulses. Then they said, okay, let's shine these two pulses together, now that they are generated, into gas again, right? Oh, too much? Okay. So, and when you shine it to the gas, these XUV pulses kick out an electron, right? And then, so this is the electron which is kicked out, right, with this momentum. And then depending on where in the electric field of the laser this electron is kicked out, you get another part of momentum that it adds up, right? So then you steer the electrons which are kicked out from your atom. Then if you look at this video, you see how the whole process happens. Okay, so now the laser pulse comes. These are the atoms, right? So this is your XUV pulse that now is going to be close to the atom, right? Now it hits it, the electrons are kicked out, and then their direction is changing relative to the electric field of the laser that you have. And then you can start to measure the spectrum and see how short they are and do some data analysis to extract the data from it. So that was also a very important measurement, because how to measure such a short and fast things. So then this slide brings us to the ultra-fast technology of 2000, right? That we can do attosecond spectroscopy. And you can see that people can, for example, this paper is a very good example, that they can look how the electron dynamics is changing around the core atom. Okay. So this brings me here, right? About what laser was used, what kind of laser people are using now to generate attosecond pulses. No question. Are you sleeping? No? Okay. So should we move on? Okay. So now I would like to talk to you a little bit about solar lasers. So this is it's kind of an old and new topics together, right? Topic together, because people built the first solar laser very early, and then somehow development stopped on it. But now, again, it takes momentum. So what I do, I just try to motivate you why this is an important topic, and then we'll show you what is the state of the art, right? And what needs to be improved to be practical. Now you know also how to build lasers, so. Okay. So this is our solar system, our planet, right? And then we get the energy of the sun for free. I just put some numbers together, right? The light that we get from the sun, right, in 1.5 days, it's equal to 3 trillion barrels of the oil reserve on the planet Earth, right? So if we manage to harvest the light of the sun properly, you can forget forever about the oil, right? And then the total energy that it's used by the whole world in 1 year, sun can provide it in 1 hour, right? So it's important to use it and harvest it. But where do we stand? At the moment, 80% of the total primary energy of the world is coming from the oil, right, and fossil fuel. And we know that, right, that the world energy demand will be doubled by 2050 and will be tripled by the end of this century. So we simply have to think, right? And sometimes it's hard to think about hard subjects, but we have to do it. And the solar lasers is one of these hard topics. How much we consume? I mean, there are these solar panels, there is wind energy, right? If you just put the numbers, you see that from the point of solar energy consumption, we use 0.015% to produce electricity, which is very pathetic, right? 0.3% to heat things, right? We focus the sun to heat water and so on. And 11% of the solar energy is used by plants for the process of the photosynthesis. Do you know what is photosynthesis? Yeah. So at the end of my talk, I come back to the photosynthesis process, right? So the plants get the light, and during the photosynthesis process, generate energy. And the process is very surprisingly efficient. So if you have a leaf of a tree, the amount of sunlight that comes to it, it can convert that solar light to energy by 30% efficiency, which is very nice, right? So it just tries to absorb as much as possible, probably happened during the evolution. And it's also interesting to see that more of all the green plants that they are around us, they only consume 1% of the solar light. Most of the solar light is just consumed by algae and kind of bacteria, right? So that's why when people panic about the health of the oceans and seas and, oh, we need them, we need the oxygen and stuff, it's because they are really doing a lot for the nature. So, what is the sunlight, right? If you want to describe the spectrum of the sunlight, the way that you describe it, you can describe it with a blackbody radiation. What is a blackbody radiation? It's the light that is emitted from everything with a temperature, right? So if you look at the lavas, for example, you see these colors because it's so hot that it can emit visible light. You also emit some electromagnetic wave, right? They are in infrared. If you have an infrared camera, you can see each other. And these type of radiations, they are called blackbody radiation. Everything emits electromagnetic field. How the blackbody radiation scales, look at this graph, right? Here I have the wavelength, and here I have the intensity. So if I make an object hotter and hotter, increase the temperature, then you see that the amplitude increases, and I'm also generating higher and higher frequencies, right? So if you have an object which is 5,000 Kelvin temperature, it has the 5,000 Kelvin temperature, then it radiates at visible. Okay, it's just so hot that it generates visible light. So it was so hard to explain this process. I mean, scientists were very confused also how to explain the blackbody radiation with their formula. Maybe you remember it from your lectures, right? And the whole mystery was solved by Max Planck in 1918 when he said, okay, let's assume that the light is made of quantas of energy, right? And then the people could fit these curves together, and now we have a formula of blackbody radiation and so on. Just to connect it with what you had in your lecture probably. Because the classical theories, they were just saying, oh, okay, this is what the classical theory could predict, right? Okay, let's see. Okay, so I just said that if you have a temperature of 5,000 Kelvin, you can radiate visible light, right? What is the temperature of sun? It's around 5,900. And if you just plot the blackbody radiation for the sun, you see this yellow curve, right? So you need a hot object to radiate for you. So this is what you see in space. But if you want to look at the sun on the planet Earth, you see this curve, the black one, right? Why? Because we have an atmosphere, and the atmosphere absorbs part of the solar light, right? So we know that we have this ozone layer, for example, that really just reflects back and doesn't let this ultra UV light to come in. And then at longer wavelengths, the molecules in the atmosphere absorbs light and so on, and they scatter. So what we get is not what is there, right? And if you want a number, then the solar flux that comes to the planet Earth is about 1,400 kilowatt per meter squared. But what we have after the atmosphere and so on, we have about like 600 kilowatt per meter squared, depending on where we sit, right? Because world is a big place, right? In some places, we have high humidity, and water absorbs a lot. If you look at the absorption spectrum of the water, it's from almost visible to mid-infrared, right? So if you are in a very humid place, then you get less of the intensity of the sun coming to you. And it's also, we have days and nights, right? So this is, we also have clouds. Clouds also scatter so much of the light, and if you have a cloudy day and you want to use the solar light, you are gonna face some problems. Okay, so now we know that the sun has a spectrum of a black body at 5,900 Kelvin. But let's see what kind of light it is, right? With the lasers that we use, we know that they are very coherent in space and time. But what about solar light? So we know that it's incoherent in time, right, temporally. It's not like a laser, right? It's an incoherent light. I think with around 1 femtosecond of the coherence, that it has a very short coherence time. But how is it in space? So I think in the workshop yesterday, you just played a little bit with the slit and double slits, right? And how diffraction pattern and so on. So now you can see how these things are used. So to measure the spatial coherence of light and see what kind of light it is, solar light, Then these scientists just had the sun and passed it through a double slit, you see? And then they looked at the fringes that shows up afterwards. Then they counted the fringes, they plotted them, and then by that they could see what is the degree of the coherence in space, right? It's important, especially if you want to focus it, and so on. It gets harder and harder. Then you can see that, for example, this is the result of their experiment, that if you have a sunlight in a very nice day, then you have almost up to 50 micrometer coherence, right? So the sun in space is not completely incoherent. You have partial coherence. And then you lose the coherence quite fast afterwards. The fact that it's partial coherence is that because it just comes, the light comes from very far away to us. And when the light reaches us, you almost have the plane wave at the surface of the Earth. So then they repeated the experiment for different scenarios, right? That if you have a foggy day, if you have clouds, right? What happens to your light? And then you can see that you immediately decrease the visibility and the amplitude of the coherence. So it's good that it's partially coherent because it should make the life easier for focusing it, right? If we want to get high intensities. Okay, so you can do a lot of things with solar lasers, but with all these problems that I told you, right? That there's lights, nights and days, there's cloud. What kind of applications could be still super interesting and super important that it makes sense to go through all these difficulties and try to make a good solar laser? So then I have this cartoon. This is from a kind of review paper that we have. I mean, it's going to be at APL Photonics very soon. I think next month is going to be out. Then in this cartoon, you can see what are like these 4 big options that they are so important and it makes sense to dedicate our life somehow to the solar lasers. So one of them is that we have these photovoltaic cells, right? That we use to convert sun to energy. When you use a photovoltaic cell, you don't use the whole spectrum of the sun, right? So there are just some particular wavelengths that interact with the photovoltaic cells. And they are not necessarily the best ones that they go through atmosphere. And then people in this business, they did some experiments and they see if you have a coherent single color light, go to the photovoltaic cell, you get a very higher efficiency, right? The whole thing is that you want to have a high efficiency. Then one way to just make the performance of them better is to just get the broadband solar light, convert it to lasers, and then feed the photovoltaic cells, right? Because then they are going to be more efficient. But then you might say that, okay, I mean, if you have a laser, right, I mean, we are going to talk about it, you have to track the sun, right? The sun moves. So then it's very tough, right? And you have days and nights and so on, how to do it. Then there was this scientist in NASA, I think it's around 1950, if I'm not mistaken. I talk about something else in between. Okay, I go back to this. So that he talked about the concept of a space-based solar power. You can see that people somehow also made a cartoon out of it. This is a animation that you can watch in YouTube. This is a series, right? That shows scientists sitting in a spacecraft which is orbiting around the Earth, right? And they have solar panels. They get the energy, convert it to laser, and then they send it back to the planet Earth. That was the idea, right? So this gentleman just calculated that if you have a satellite around the Earth, and just with your satellite, you manage to get, because their You don't have the problem with tracking the sun. You don't have clouds. You don't have atmosphere, right? Everything is perfect. And you just harvest the energy of the sun, convert it to microwave or laser, and send it back to the earth, and then use photovoltaic cell to change them to electricity. He showed that you have a higher efficiency, and it makes more sense economically and in terms of what you put and what you get out, right? So that was his idea. But it was on pause for a very long time, right? Because we were not so advanced to put things in the orbit. Now, I don't know, Elon Musk is doing a lot, so it's a very active area at the moment. Now, after many years, people are just picking up on this idea again, right? NASA is picking up, the Space Agency of Japan is picking up, and also the European Space Agency in Europe also tries to develop such a system. And also there is also so much development in China. So let's say that you have your satellite, right? You harvest the sun, and you want to, then you beam it to the planet Earth, and then here you can feed your vehicles, your, I don't know, houses and everything. At the moment, the scheme that is followed is based on microwaves, okay? So the idea is to get the sun, turn it to microwaves, and then beam it to the Earth. Why microwaves? Because they have a very high conversion efficiency. So you can convert the sun by 80% to a microwave light, right? So it makes sense, right? You just have 80% efficiency, it's perfect. But there is a problem. I mean, Alessia yesterday told you about the diffraction limit of light, right? That if the wavelength is longer, the diffraction limit is also bigger. So microwave is a very long wavelength. And if you want to beam it on the Earth, then somewhere I have this 4 kilometers square. Yeah. Then you need, I mean, you, at the best case, the diameter of the beam is gonna be 4 kilometers, right? And if you are an inhabitant, you never want to walk in this region, right? So it's like so much microwave coming to the Earth, right? Very high intensity. Also, if you think about it, then we have this radiation on the Earth, and it's also changed the ecosystem. I don't know, the animals are gonna go away from it, the plants are gonna die, and so on. But then, the idea is that if you use a laser, then the wavelength of light is much shorter, then you can focus it much tighter, then you need like meter squared areas, right, to get the beam to the Earth. Then it makes sense, right? Then you have a big detector, get the light, and you can move on. But the problem is that the solar lasers are not efficient. Okay? I mean, I'm gonna show you a lot, but at the moment they have like 1–2% of efficiencies, right? And you cannot, I mean, it doesn't make sense to spend so much money, put them in the orbit, and then get 2% of the light converted. Okay, so I have to go back to this one again, right? So this is this scheme, right? That you have the solar laser in the space, and you can send it to the planet Earth. Then all these space people, they are also interested in solar lasers in principle, because if you want to do mission on other planets, or if you want to communicate with Mars, for example, right, then you need something which is sustainable. You need something that can stay on Mars, gets the energy converted, right? You don't have human there to fix it for you. So then it's also very important to develop good solar lasers for interplanetary communication. The other thing is the topic of the energy, right? So there are these cycles which are called sustainable cycles of energy production. I mean, maybe you've heard a lot about hydrogen economy, right? People were talking about, oh, let's generate energy from some chemical processes with hydrogen and it's clean, right? There is also another type of economy which is called magnesium economy, which I showed here. What is magnesium economy? The Japanese scientists worked a lot on this topic. Toyota also invested so much money on it. Magnesium economy is based on magnesium. Why magnesium is important? Because it's the 8th most abundant element in Earth, right? So we have so much of it. Good. And you can find it a lot in seawater. That's why the factories are most of the time beside the seas, right? It's relatively light, so if you want to transport it, it's not also, because it's kind of a metal, right? It's not a huge problem, and it has a 10 times higher energy storage than hydrogen. So if you manage to do some chemical processes to release this energy of magnesium, you are 10 times more efficient. So just very briefly, a bit of chemistry, I promise. Just 2 formulas, right, that to show you why the solar lasers are important and where they can be used. So the whole thing is that, the first thing is that magnesium, you can't find it like isolated magnesium, right? It's always combined with something. You have MgO, right? So it likes to interact with other atoms. So if you have magnesium now, and you mix it with water in a chemical process, right, the chemists do it, then you can release this amount of energy, right? And then the hydrogen which is generated here, this is called hydrogen economy, you can mix it with oxygen, you get water, and then you release again energy. And these energies these are clean energy, right? You can use it for electricity, whatever you like to do. So then during this process, right, you generate this MgO, because magnesium likes to attach to something, right? And you need to reduce it again to magnesium. When the chemists want to do this process, they need 4,000 Kelvin temperature in their, I don't know, high pressure tank or something to do this reaction. You see, it's a very high temperature. Sun is 5,900, right? And there is a method that they use to do this reduction, and at the moment, they are using, let's say, non-sustainable sources, right? And now the idea is that if you can use solar lasers, they like lasers because they say that it's more efficient for them to heat up the whole thing. At these 2 stages of the chemical reaction, then you have a sustainable cycle. What does it mean? It means that you get water into your factory. The energy of the factory comes from solar laser. You generate energy, water, hydrogen, and then you reduce it again to magnesium. Then you can close the cycle. And it's a very environmental friendly cycle, right? So then it's important to have a good solar laser, right? And they've worked a lot actually on developing and polishing the solar lasers to increase their efficiency and so on. Okay, so now let's see how to build a solar, and what are these problems, why it's not efficient and so on, right? Yesterday we talked about Ruby, that is a 4-level laser, right? So in principle, with a solid state gain media, you can get lasing from them in 4-level or 3-level geometry, 3-level atomic structure. So how does it work? Now you see a 4-level system, right? You pump your solid, right? In this case, let's say that you have an ND-YAG laser, which is a 4-level system, and it's also very common because you can pump it with a flashlight. So then you populate the higher level, right? Then over time, part of this population just comes to the lower level, and then you put your cavity here at this frequency, okay? Then you have a spontaneous emission, then your cavity is at this very specific frequency, and then you lace, okay? So when you have a 4-level system like this, the lasing threshold is low. What does it mean? It means that you don't need so much pump to do population inversion, right? If you want to have the laser, you need to have more electrons on the higher level, right, that they want to come down. And because there is a bit of time delay here, with a lower pump intensity, you can kick the electrons up, right? You don't need so much high intensity. But there are many good solid-state gain medium, right, like ytterbium YAG that we talked about it yesterday. They are 3 levels, right? So this level doesn't exist, and it's very close to this guy. Then you need a more intense pump lasers to do so. So, and we know that the sun is not coherent, so it's really hard to make it intense. Okay, so the first solid-state solar laser was developed in 1966. In 1963, people developed the first liquid gain medium, right? The first solid-state was developed by Young in 1966. You can see him, right? He's standing. It's a very nice picture in his article that in old days, apparently people took the picture of themselves in their paper, which is interesting, right? And then you can see that he had a giant device, right? Why? Because he gathers the light, the sunlight. I mean, this is like one of these telescope mount, right? And you need to track the sun, right? Because you want to focus the light to your gain medium, and you want to keep the focus on the gain medium. So you have to track the sun. And it's motorized, and he tracks the sun, and he can get 1 watt of power. And the gain medium that he used was a 4-level system in the YAG. And if you look at these papers, these very early papers, you see that the main issue with the solar light, I mean, although it's partially coherent in space, is to focus it tight, right? Because unlike the laser that you can put a lens and get a very nice focus, in a partially coherent light, you have the K vectors, right? They are coming at a bit of angle. So it's really hard to put them all at one spot. So focusing is one of the biggest issues. That's why people came with so many ideas, right? How to fix this focusing geometry and how to increase the intensity of the light, of the solar light on the crystal. Then you get a better laser, right? Here you can see, for example, 2 types of technique, right? So you can have this, well, it's also very clear. The bigger your lens, the more sunlight you gather, right? So everything scales with the lens. So if the area is big, you can gather more sunlight and you can focus it more. So these are like this giant Fresnel lens. Fresnel lenses are good. I think you've seen it in your optics lecture, right? You can make it out of plastic, and it's not heavy, and it's cheap, right? And these are the ones that, for example, they are developed in Japan, that you can get the light, direct it, and then they direct it to a kind of curved surface. Yeah. Ah, perfect. So we are really now in harmony, right? Accidentally, let's say. Right. I mean, you've heard about it, the concept of the Fresnel lens yesterday. They are really actually important for, I mean, for many applications also, in cars and stuff. Okay, so now this is called the primary light collection. It's just that you have a big area to collect the light and focus it to a spot, right? But you want to increase the focus. You want to focus it tighter. Then you need the secondary light collection. And this is really tough, because if you put a lens, you don't see a focus. It's not coherent, right? Then people started to use compound parabolic concentrators. If you are in the solar energy business, you've heard about CPCs. They use it a lot, right, for thermally heating liquids with sunlight and so on. And it's interesting because these CPCs were designed by a scientist for nonlinear optics. And then when people wanted to do solar energy, went to the business of solar energy, they just saw, oh, there's a good design that might help us, right? And they just took this design. So how does it work? Look, it's only two parabolic mirrors that they are sitting together. And then you can put your gain medium, for example, at the center of these parabolic mirrors. Let me see if I have this. Yeah. They are called non-imaging lenses. Why? Because you lose phase information. If you look at the light which is coming out of these CPCs, you don't have the Fourier information anymore, okay? But you just bring intensity of the light together. See that the light is just gathering at this point, right? Just reflects back, back, back. And then people developed it further and further. For example, you can mix two of them with different refractive index, right? To just focus more and more. I mean, this is similar to what Alessia was showing for the microscope objectives, with the difference that there you really have the phase information and everything. Here you just gather the intensity to a small spot, right? It's like a tube, but it's so hard to make them actually. Right, so and then if you put your gain media somewhere here, then you have a small focal spot, right? Okay. Then if you look at the literature, you see thousands of them, right? For example, you can come with different geometries. These are kind of like a waveguide, but big waveguide at very specific angle that you have a higher chance to trap the light. So it's all about how well you can trap the solar light to a very small spot, right? And then you can have your laser gain medium here and pump it from the side. Okay. Let's see. Oh, okay. Okay. So then by using these techniques, yesterday I was talking about the problem of heating, right? If you don't convert all your photons, of course, to the laser, which you don't, then the rest are gonna turn into phonons, right? And then heat up your gain medium. So you have to cool it down also, right? And this heat problem is actually an issue in solid state lasers, right? So then you can see, for example, this is one of the successful design of the solar lasers. There is this paper in Nature Photonics. It's a review paper. Or it's like a summary paper. It's a very good one. I put my slide. I'll upload it that you can have access. So if you are interested, just have a look at this paper. It's very interesting. That you get the solar light, you have the Fresnel lens, you focus it, then you have a secondary lens somewhere, right? And then the whole thing is in a kind of, I just don't want to use the word of cavity, but it's in a kind of tube that water can go in and out and remove the heat, right, from your gain medium. And so this is your gain medium, right? And here is the, let's say, the output coupler of your laser, right? So you can have a very simple geometry. And then here, this scientist just coupled the output of the solar laser to a fiber to just transport it easily to other places. This is what we built in Erlangen. So actually, it was, so we started the project just like as curiosity, and now we are doing some other stuff. But we had this very big Fresnel lens and the tracker already, and then we thought, okay, let's build the solar laser. So you can see this is a 1.4 by 1.4 meter Fresnel lens that we got it from Japan, right? The cost of the transport from Japan to Erlangen was higher than the actual cost of the Fresnel lens, right? So, and then you see that it's mounted on one of these trackers, and the gain medium, and the light is focused somewhere here, and then we have the laser cavity here. So how the cavity looks like? So we have the secondary collection of light, which is with this object, right? We just designed, it's a combination of a CPC and a ball lens. So the light comes to this ball lens. The ball lens has this advantage that it can trap quite well the light with different K vector, right? And then it's sent to this CPC type collection, and then we have a very, like a fiber waveguide geometry at the end to deliver the light to the gain medium. And then this is the design of this holder that we use for the cooling of the solar laser. So you can see that the gain medium goes inside, and the whole thing is cooled. And if you look at this from inside, we also have this geometry again inside to trap more light, right? You see that it's gold coated to just, that if there is a bit of sunlight here, then it reflects back and it's guided again to the gain medium. So this is now operational at our institute if you stopped by, right? I mean, we bring it inside because we don't have a house for it, but we can show you how it's built. But for sure, this has to be improved, right? The efficiency is still 1%. And you want higher efficiency if you want to talk seriously, let's say, about solar lasers. Right? Okay. Before I go to this, any question?
I have one question here.
Mm-hmm.
Interesting presentation. The solar resource potential in Africa is great. Hence, the research on solar pump laser is a novel concept to the region. What is the solar irradiance range are we targeting for optimal operation? Okay.
What is the solar are we targeting for optimal operation? So the total solar irradiance in the space, right, from the sun that we can get around, let's say, planet Earth, is 1,400 kilowatt per meter square, right? And then if you manage to have your solar laser outside, this is the flux that you have, right? So if you focus it, then you can, the better you focus, the more you increase the intensity, right? This is per meter squared, so if you focus it to millimeters squared, then you have 10 to the 6 times higher intensity. This kind of, so if you are on the planet Earth, right, because of the atmospheric absorption, in Africa it's much better. I mean, Erlangen, we barely have sun here, right? I mean, we did magic that it runs, right? In summer. Okay, in summer it's good. But still, I think I have a slide because the planet Earth is tilted, right? It's not, so we are not like this towards sun, it's a bit tilted. And if you calculate this tilt and stuff, then the number really goes low, right, when you are on very north or very south. But let's say in the best case scenario, you get like 650 kilowatt per meter square. Watt per meter square. 650 watt per, that's 1,400 watt per meter square. So you go to 600 something. So let's say that we had such flux, we measured it. Then we had to focus the light to, I think the focal spot was about 3 millimeter. So then you can calculate the intensity, right? 600 watt per meter squared, what is the intensity at 3, 4 millimeter? And that, at that intensity, we reach the threshold of laser. So somehow you are fixed with the irradiance, because that's what sun gives us. But what you need to increase the area that you collect the sun, right? Then you collect more and more energy, and you need to find a way to focus it tighter and tighter to reach the threshold of lasers. So this is for the case that you want to do conventional solid-state laser, right? You need population inversion and so on. Now I'm going to talk a little bit after questions about this wave of scientists, us among them, that they are trying to design gain medium that they work at low threshold, right? Low threshold lasers, let's say. Yeah. And then I'm going to cover that after this Q&A part. Questions? It's here. I can pass it to you.
Thank you so much. I think mine is just a comment, especially to do with the efficiency, the conversion efficiency. I mean, with the solar, we are talking about this whole range of spectrum. I mean, visible, infrared.
Yeah.
But now the gain medium that we are going to illuminate, I mean, we have specific transitions that are going to absorb just a small portion.
Yeah, exactly.
So I think when we have the 2% conversion efficiency, probably it is not so bad.
Yeah,
Because
exactly.
if you are just considering the small portion that is going to be absorbed, probably it is even going to be higher. And even quite a number of lasers, the conversion efficiency is also not very high.
Yeah, exactly. So you are talking about, I mean, 2 slides I reached this topic exactly, as you mentioned. So the whole thing is that the way that the conversion efficiency is calculated, because what people care is that I get this much of energy, how much of it you can convert, right? So then that's how they say 1% of the solar light, right? But in principle, you always have narrow transitions that you can pump. And this is the part that can be improved. This is one of the ways that people are working on it, exactly. But if you just consider that portion of the sunlight, which is converted to solar, to laser, then it's okay, right? We are doing good. It's just when you just consider the whole sun, then you think, okay, we should do better with the solar energy. Exactly. Yeah. More questions? Comments? Okay, then we move on maybe. Let me see. Okay. Right. So now let's see where we stand, right? It's always important to know where we are, and then from there we can decide where to go, right? Or what needs to be improved. So this is the first laser, 1 watt. And then just look at the spots, right? Here I have the air, and here I have the output power of the lasers. So the first laser was 1 watt by Young, the first solid-state laser. So these are only about solid-state lasers. And then you see they have Nd:YAG, because it's 4-level. People just kept using Nd:YAG because it's easy to reach the threshold. But it's also not a very good gain medium, right? It has many problems. You cannot dope it very high. So we can do better, right, if you focus on it. Then if you look, there are 1, 2, 3 demonstrations, up to 2,000. There are not so many people working on it. And you see, even the progress was exponential at that time, right? And the reason that people didn't work on solar lasers, because when the laser was invented very soon, they learned that they can use a laser to pump a laser, right? So for example, ytterbium thin disk lasers, the pump was a diode laser. And the diode gets the electricity, turn it to a laser, then we use that laser to pump ytterbium, right? And it's easier, right? You can focus it, more efficient, nicer. And of course, then you always go to the easy path, right? Why to bother? That's why there were so few measurements. But then you see, just look at this part. Since 2000, there are zillions of data, right? And it's only now the care for the solid-state lasers. There are also other type of lasers. And that's because we feel the problem with the energy, we feel the problem with the climate change, and I think we admitted that the easiest path is not always the most correct path, let's say, right? We have to be more aware about our surroundings. So you see that there are many dots for Nd:YAG, and there are some gain medium which are like chromium Nd:YAG or cerium Nd:YAG. I'll talk about them in a bit. These are a kind of gain media that people used to increase the collection efficiency, as Geoffrey just mentioned, right, for the pumping. So it's like dual doped kind of gain media. So the host material is YAG, then you have Nd ion, and you have chromium ion to transfer the energy. We are going to talk about it. Right, then you see how you do, right, in terms of if you increase the solar radiation, if you have a bigger Fresnel lens, you collect better, you focus better, of course you can increase the output power. And then you can go to 80, 100 watts, which is quite lots of energy and power. But one problem is that to control the quality of the mode, these are CW lasers, And the mode is nice, the mode of the laser, if you take care of all these thermal issues and heat problem and have a nice design, right? These lasers, they are all, most of them multimode. And if you want to think about interplanetary communication from Earth to, I don't know, Mars, then you want a single mode laser, right? You want a very good beam quality. Okay, so now back to the comment, exactly this slide. Let's look at the very famous gain media, laser gain media. Now I have these two curves. These are all in this review paper that you can later on also read. Here I have the different gain media which are very famous, right? And most of the laser developers use one of these gain media, solid state gain media. And here I just show you the absorption spectrum of them. These are the transitions that they absorb light, right? And where they emit. So if you want to send a laser from space to Earth, then you want to have it laser at a wavelength that goes to the, travels through atmosphere with the minimum of absorption, right? Because you just don't want to lose light while propagating. So the emission is also important, where the laser emission is. And this is the spectrum of the sun, look, from 300 something down to 2-3 micron, right? So you see it's broadband. And now I'm just showing this part. So I'm just showing this part of the spectrum. Okay, the very cool thing, so one of the gain medium that we talked about is Nd:YAG. You see? It doesn't absorb so much. It has just this very narrow absorption band. So we don't really use all the spectral components of the sun, right? But look at titanium sapphire. This was the femtosecond laser that we talked about yesterday, right? Was the jewel of the crown of laser history somehow. It has a huge absorption bandwidth at 500 nanometer. And if you look at the peak emission of the sun, it's at 500 nanometer, right? So here you have more intensity at 500. So if you can have a laser gain medium which absorbs at 500 nanometer, it's beautiful. And then it emits at 800 nanometer. And 800 nanometer happens to be one of the most efficient wavelengths that photovoltaics, I mean the new photovoltaic cell works. So they want 800 nanometer wavelengths to work very high efficient. Okay, so this looks very, interesting, right? But no free lunch. The titanium sapphire is a 3-level system. So it's so hard to reach the laser threshold, right? You need to focus the light so tight to just make it to laser. That's the price, right? So if you find a way to focus the light very tight beyond the current technology, then this is beautiful, right? And then you can think even about a femtosecond solar laser, right? So if you look at the Nd:YAG, you see that the emission is also very narrowband. You can get nanosecond pulse laser if even you want to think about pulse operation. The other one that I want to talk to is this ytterbium YAG, right? Ytterbium YAG absorbs at 950, but emits at 1030 nanometer. And it is very atmospheric friendly in principle. And it's a good crystal. So it's a very good gain medium. You can dope it high up to 10%. But of course, it's a 3-level system, right? You have to focus the light tight. So these two, for example, out of this list, we tried, with simulation, right? We tried, specifically, we worked on the ytterbium YAG and titanium sapphire. Ytterbium YAG, it has a lower threshold. It's easier to force it to lace, but titanium sapphire is still hard, right? But think about it, that if one can, or chromium, for example, this is also beautiful, right? If one can bring these guys to lasing, then it's all very nice, right? So this is the work that can be done, for example, to optimize the gain medium that you have. So how to increase the efficiency is like how to increase the efficiency, not to increase. So people thought about this dual doping to increase the efficiency. And what is the idea? The idea is that we just talked that the Nd:YAG is absorbing here, right? So then they thought, okay, if I put if I dope my crystal with 2 ions, Nd3+, for lasing, and then I also dope with cerium. So it's like in the crystal you have these 2 ions, right? And then if you look at the absorption of the cerium is at shorter wavelengths at 500 nanometer, so it's a very nice wavelength. Then I can absorb the solar light at this wavelength in cerium, pump the electrons, right? And then I can transfer this pumped energy to Nd ions in my crystal. And then they lace, right? So this dual doping worked actually very nicely. They could really show, that you can get the lasing at the lower threshold and with higher efficiency. But also still has its own problem. Then there is a crowd of people who are working on low concentration lasing. These are the group, and also my group among them. We are thinking about finding a ways, developing a new gain media that doesn't have a high lasing threshold, that you don't have to focus the sunlight so much, right? And the idea is that if, like photovoltaic cells are so successful, right? And part of their success is that the sun just can shine on them and they work, right? So if you have a laser that doesn't need a lens or a Fresnel lens or the secondary collection, anything, right? That sun shines on it and it lasers, then that's when we are talking, right? Because it's much cheaper, then it's not sensitive to the direction of the sun. You don't have to focus so tight, right? Yeah, so that's one of the, for example, passes that scientists at the moment, I mean the solar laser people are trying to motivate. So this is a work which is done by my colleague in Karlsruhe in collaboration with Japanese. Japanese actually are doing a lot in this field. And then they somehow picked the idea of this dual doped crystal that to transfer the energy to this kind of geometry. So what they had a system, it's like a freezer that cools the gain medium. Then I don't know if you see, there is fiber, right? There's a bundle of fiber that is just kilometers of fiber that it's placed on this cooled surface. And they have some dye solution with some nanoparticles and stuff that what happens is that the sunlight shines on this, let's say, laser, and then the dye absorbs the light with a very good efficiency and transfers the energy to the this Nd fiber. I think it was the Nd fiber, right? And then this is the kind of fiber laser that I think Nikolai is going to talk to you about the fiber lasers on Friday, right? So it's in principle a fiber laser, and then this way you can pump it. And what they show is that you can really bring this to lasing at one sun. That's the language, right? One sun means you don't need to focus it, okay? This is really a low threshold, low concentration lens. For example, the laser that I showed you, that we built in Erlangen, that needs 7,000 sun, right? So you see the improvement here. Okay, but there is always a but, right? Otherwise, we were not sitting here together. One of the things is that you have to cool it down. Okay? If you want to think about a sustainable system, you don't want to get the energy of the sun and use the electricity also to cool. You know, it's just why, right? So then you have to fix somehow this part. And also, the efficiency is also like not that high, right? You can improve it and make it better and better, which I think they are doing at the moment, actually. So, what we do, this is now, I'm talking about a project that we have in Europe. This is with 5 countries involved, right? It's a very big project. We are also trying to develop a new gain media for low threshold laser, right? That you can have sun and lasing with no focusing. And then what is the idea? The idea is very inspired by nature. So I talked about photosynthesis, right? The photosynthesis is a very efficient process that nature has to harvest the light, the solar light. And it's all because they have, if you look at these molecules that they are, or the aggregate that they are involved in the photosynthesis, you see that there are these kind of structures that they harvest the light and they pass the energy to the center, right? Then for the photosynthesis process at the center, some other stuff happens. But what we are thinking about, we are thinking to replace, to remove, I mean, to have these molecules, these aggregates, let's say, and then to put the ions, the neodymium ions, right, or this gain media, like in nano dimension, inside these giant aggregates, right? Then what happens, they just, so you shine sun, they absorb the sun very efficiently, and then they pass the energy to your gain medium in the center, right? And if you look at the these levels of the energy, then you see how it works, right? So these aggregates, in principle, absorb from sunlight and then pass the energy to the laser gain medium. So this is the topic that my group and 4 other big groups are working on it. And then on top of that, there are also, we also think about using bacteria for lasing, right? So because if you are in space, you want a sustainable gain medium. Bacteria, they live in space. They don't need us to live, right? And they can reproduce themselves. So then you can have a sustainable laser that the gain medium reproduce itself and also can lase maybe. So this is what the current activity on the solar lasers that we have. We are also doing some design. For example, we are trying to, I mean, we have a design, the paper is going to be out soon, to have a kind of ytterbium YAG thin disk solar pump laser, right? To help with the heat removal and so on, which are very, I find them very interesting topics. Okay, so then with this, I would like to end my talk and my lectures, and maybe we all take the not easy way, right? And push this solar energy harvesting more. Okay? Oh, thank you.
Thank you for the nice presentation. I have a question. You are dealing with very, very high quantum energy, non-monochromatic light, also thermal relaxation, and strong thermal lengthening effect that affect the beam quality.
Yeah.
How do you correct this thermal lengthening effect?
So exactly. So the whole thing is the heat problem, right? The very famous heat problem. So this is the laser that we built, right? So we had a rod in principle inside, and then we tried to capture as much as sun. And then you can see that, I don't know if the design is in my slides or not, but, oh, maybe let me try, maybe. Oh no, this is another talk, okay. So, so what we saw is that, for example, you designed a cavity to have a, I don't know, 30 centimeter cavity, right? And then when you are outside, it doesn't work at 30 centimeter for sure, right? Because you have thermal lensing and the cavity mode is different now. So then we had one of the mirror on the stage to bring it to lace, right? And that was actually the reason that we started to look at the thin disk geometry. That was exactly because we worked with it and we saw that there is so much heat problem. And then we thought, okay, there is this thin disk concept out there, right? And we have some simulation. Now we are putting the manuscript together that if you, exactly like the yesterday talk, if you have neodymium YAG even, not ytterbium YAG, in the thin disk geometry and you cool it from the back, then the whole thing is more stable. And then what we did actually for that geometry is that we have a dome on top of the thin disk, that it's just coated from inside for the pump wavelength. So we trap the pump that goes back several times through the gain medium. And that way it worked, I mean, it worked much better in terms of deformation of the gain, because you also have these deformations, right, that make your beam quality, destroy your beam quality. So with the thin disk, you can see that you can go to the single mode operation, really. Because these are all multi-mode, right? You have several modes that come out of your laser because exactly of these heat issues.
Calculate the thermal lengthening, for example, the focal length, the thermal lengthening, using additional optics also, maybe.
Yeah. If you have a fixed geometry, then you can think about it ahead, right? But then again, you get this, somehow this deformation on the gain medium, on the set, then it destroys your mode. Because it's just the sun is not coherent. No, I just say this because then you know the value of a coherent laser, right? That you just put a lens, it's focused nicely to one spot.
Incoherent, spatially incoherent source. And I wonder what is have people thought about what is the limit, how far can one go? This is the first part of my question. The second part, I was wondering whether one can do something about it to circumvent. I mean, it's almost like trying to violate the second law of thermodynamics, but sometimes it helps to think about things which seem not to be so easy. So do you see any possibility to kind of make the sun effectively more spatially coherent, so that as a result probably also the efficiency can go up? Are there some thoughts in this direction?
Yeah, so this is also what we thought about, actually. We were thinking, okay, the spatial coherence is a problem, right? That's why the life is tough with solar light. Then, I mean, one has to think, and I think many people has to contribute because it's really a big stone to move, right? But this is something that we started to do with Flora Kunst at the Institute. And what we are thinking of is that if we can somehow design a topological structure that transfers the light very efficiently to a, let's say, nano-sized gain medium, that you can somehow have this low threshold laser and so on. But this is definitely something that has to be taken care of, right? I think by many scientists for sure, because it's a very big topic. And then for the efficiency, there are several work. So at the moment, I think the highest output laser is like 100, maybe 50 watts. And I think this is might be a bit higher actually. This is by a startup in Portugal. I mean, they have also quite some sun, right? So there's a startup that they are working on the solar lasers. But there are also some theory paper that shows how you can get more if you scale this primary collection, improve the secondary collection, and so on. But it seems to be, at the moment, there are these moments of life. There is my scientific life, of course also life on its own, that you feel that you are a bit saturated, right? I mean, if you look at the years and everything, you see that in the beginning it was exponential because I think people just were adding a new lens, the whole thing, narrative was changing. But if you look at these spots, you see that these are all small improvements. So it's like that we are a bit saturated. So it means that you need a new push, right? A new idea how to make the maybe solar light more coherent also. New gain medium. And I think many people from different fields actually can contribute in that, because in this project that we do, we have, I mean, part of the team are these biologists that they make this photosynthesis molecule. So I think it's really a big teamwork, collaborative problem to be addressed.
Any other question?
Hi, thank you very much. It was really a nice talk. I would like to know a little bit more about the low concentration.
What is that?
No, I think I understood more or less the concept. If you go back to the slide.
The 411?
The low concentration lasing.
Ah, the low concentration laser.
Yes.
This one. Right.
So the first design, the active medium is a dye.
Yeah.
So the dye lasers are coming back.
So the dye solution is only there to absorb the sun,
Okay.
and then it transfers the absorbed energy to this ND doped fiber.
Okay.
So the fiber is the gain medium. So it's just like an intermediate step, right? And then this works pretty well, right? They absorb very nicely, and then the fiber is really long, right? It's several kilometers. So if you increase the gain medium, then you have more atoms that you can use for lasing, right? That's beneficial. And so it's also fiber geometry, so it removes the heat, releases the heat easily.
Right.
And that's why they had to put it at the end on this Peltier type cooling to get rid of this heat also. Because, I mean, when I talked to Bryce, and he says that if you room temperature operation, it doesn't laze because of all these problems, the thermal lensing. And you have to really remove the heat. And I think in their first demonstration, they had to use, I don't exactly remember the number, but it was like like 10 suns or something, with a little bit of focusing. But in the recent work, it's really one sun, right? It's just no focusing.
And the overall dimension is that scale bar is 50 millimeters.
50 millimeter,
Okay.
right? Yeah. So it's not big.
Yeah,
so what
that's
this group actually are aiming, their aim is also very beautiful. So the idea is that if you can have flat solar lasers, you see it's a flat system, right?
Yes.
Then you can distribute it on a surface.
Yeah,
right? And then, and if it's fiber, then you can coherently combine the output of all these fibers and get a high energy thing. So then you can have a big area, I don't know, even in space it matters, right? You can put it on the spacecraft that they laser, and then there you get the laser. Coherently combine the output. But I think they are very much focused on room temperature. I mean, actually it was also very interesting for us when we started this, because the life is very different in space. It's cold.
Sure.
Right? So you don't have to cool things down, but you have to also make sure that these transitions have enough electrons on the, lasing medium. This should work, right? But so many of these cooling problems go away with the space operation in principle.
I see. Thank you very much.
Thank you once again for the excellent presentation. Just a thought, since the right from the solar is a kind of continuum, you have all these wavelengths, one after another. I'm thinking of a situation where that could be an advantage, even to increasing the number of modes that are going to be available in the laser cavity.
To increase the number
of modes.
Holes?
Longitudinal modes.
Modes,
Yes.
yeah.
And probably that also is going to help in generating the laser pulses.
Mm-hmm. So you mean to have a multi-mode laser, or to have several doping at different wavelengths that you can trap, let's say, lasing mode at different frequencies? That's what you mean. Yeah. Yeah, I feel that it's a problem that scientists can contribute a lot, because it's not touched very well. It was just forgotten for a while, right? So there's so many ideas that can be implemented and then change things. See, there's some fields are very saturated. This is like, you see that, there are some ideas that you can really immediately put and change the status. And the good thing is that it's also cheap, right? I mean, if you want to do attosecond spectroscopy, you need €1 million, right? But if you want to do solar lasers, I mean, Fresnel lenses are very cheap, €100, right? It's one of these sticky tape problems, right?
Thank you for the nice talk.
Thank you.
Let us thank the speaker.
Okay, thank you so much. On the side of the photosynthesis, there's a sign there you have seen that you are doing a research on photosynthesis, where you are going to do the doping through the trapping of the energy. Can you please explain that one? Because I think photosynthesis is one of the efficiency things which is being used for, that please.
Yeah. So it is, photosynthesis is beautiful. And I think if you look at the literature, you see many scientists who were inspired, I think, with photosynthesis. It's like one of the most beautiful processes that was optimized during the evolution, right? So this scheme that I have here, I mean, you get my slides, okay? So this scheme, the first time was suggested by a theorist, okay? And here I have the paper cited. And if you go through the paper, then you see all the details that how the detailed science works, right? But I just give you a big overview. So the whole idea is that if you look at these molecules, the aggregates, they are really big molecules, right? That they are contributing in the photosynthesis process. They have such a structure. And what is their role? Their role is to harvest photons as much as possible. That's why they are big also, right? So they have, their structure is in a way that they can really harvest photons and not lose them, right? And transfer their energy to the surface. So the structure is really optimized by nature, yeah? So what they do, the photosynthesis, you have the aggregate, and then they move the energy here, and here the process, then it's different, right? Then they generate this dipole, and it propagates, and some chemical processes happens, right? But the inspiration, which was suggested, this scheme, which was it's suggested by Luca Cerullo. He's in Florence. And he said that, okay, what about taking this aggregate, these big molecules? They are good, right? They are like a lens. They just gather the energy, transfer it to the center, and then artificially put our gain medium. It's like that you pump it, right? And then he calculated and he saw that the amount of energy that this aggregate gather and move to the center is enough to reach the laser threshold, right? Without focusing the light, right? So then, in principle, you need hopefully one sun, right? So then what we do at the moment, there is a group of biologists, or I think they are called chemists, biochemists, who are making these aggregates, and there is a group of nanophysicists that they are making this nano gain medium, right? And then there is another group who has a specialty in this kind of stuff, that they put the nanoparticles inside these molecules, right? Then they are going to send it to us, and what we are going to get in principle liquid, right? So that has this kind of molecules inside. And then we are going to put it in a cavity, shine sun, and see, hopefully it lasers fast, right? So then it's going to have like a little bit like a dye laser structure, right? That dye lasers were also in the liquid phase. One of the issues that you have with this kind of, let's say, gain medium is their stability, right? So because if you look, there is this pathway that goes to the lasing, but there are also other pathways that are more complicated. I won't go through that you lose energy, right? So then the best is that your gain medium is just rotating. See what I mean? That you have a fluid, that there is a current in it, right? That you always have a fresh gain medium. So this is the thing that we are at the moment developing, right? This sample holder that has the gain medium, and then we put a cavity and see if it works. But this paper, it's beautiful. I mean, it also has a very beautiful introduction to read, you know.
Let us appreciate the speaker. So we will have a break up to 10:20. Then we start the next session. Thank you. For those with posters, you see Dr. Gara. He will guide you. You go behind. Then you place your posters. Thank you.
What we are having today is an ongoing training. It has been ongoing from Monday. It's going to be 5 days until Friday. And mainly what we are training people in is the installation of solar panels and every component that comes with installations from home. If anyone needs solar PV technologies, the panels, the batteries, the charge controllers, the inverters, and so forth. So from this training, the students that you are seeing in the back view are learning the very basics to begin with, from electricity, these components, what they entail, what are they going to look for when they go to purchase such items, or even before they purchase them, what do they need to consider from the place that they want to install them into. We are an avenue of creating job opportunities for the youth that take part in this training, because now they'll go forth with the certifications they acquire. They will acquire licensing to be able to install these technologies as technicians.
This week we have a solar PV training, solar photovoltaics training. It has started from Monday, 30th of November, and it is going for 5 days. So it's ending on 4th of December. So basically, we are instilling skills on solar installations, designing, and sizing. We have about 17 participants. Most of them are students from Multimedia University of Kenya, and they are really interested to know more about green energy technologies and solar technologies. After this training, they will be now skilled solar technicians.
I'm a third-year student in multimedia, pursuing a bachelor's in renewable energy and technology. So this week we've been here in the T1, T2 training, which is a renewable energy research consortium. I'm going to be a participant. I'm here because I want to be impacted in my knowledge, and at the end of this course, I expect to be able to to be consulted according to the solar PV installation, and I expect to have knowledge of installing myself and even assembling and coming up with new ideas to impact the world in terms of energy, concentrating on the renewable energy. The experience so far is very good. It's the third day, but I think I've gained more knowledge than I expected. Right now we are doing the hands-on, it's the practical unit, and I think they're impacting very well because it's easier to understand when it comes to the practical sessions more than the theoretic. And I think it is very beneficial to me so far.
The experience is good so far. At the end of this program, I expect to have gained more knowledge, to be able to understand how to install appliances, how to choose the correct appliances, how to deal with customers and their demands. The experience has been very inspiring, being that there are more female students than male students. It's actually a great honor. So yeah, the program so far has been good.
It has been a wonderful experience as an intern here. I've been an intern for the past 1 year since the consortium was established, and it has been a continual educational and a learning process. When I see myself wearing an overall, when I see myself carrying a solar panel, when I see myself connecting a battery to power the loads, it has been a wonderful experience being part of the consortium. And next to it, we are proud and even more happy to have the first T1, T2 training, solar PV training in MMU. It has been a wonderful journey since the consortium was born, and as we can see the growth, and even having the first T1, T2 training, it has been a great milestone. It has been a wonderful reception, and the students getting, or rather the trainees getting to understand and to attach what they have in class and what is there practically. I'd like to urge those in the science and engineering courses to flood up these trainings, mostly from MMU or rather any other institution from any other company in the energy sector. They can come to obtain the skills that are in line with the trainings that we have.
This week is a landmark for us because we are having the first T1, T2 solar workshop, whereby we are focusing on our young youth, especially the science and engineering students. And so far, so good. We had a very good feedback, whereby we have a total of about 16 young men and women who have joined us in this workshop. We expect them at the end of the workshop to actually just apply what they have learned, and of course get licenses from the energy sector. At the same time, we are also working in partnership with the educational institutions in Germany, whereby we are collaborating into these hands-on skills. And I want to welcome all of you, especially those who are in the energy sector, to join us to actually be part of this consortium. The main aim is to actually equip the hands-on skills to these young, consultants. And one of the skills is the sizing, how they are going to size these solar components. As you are aware, we have had a challenge when it comes to malfunctioning of the solar components in our domestic and industrial sector. At the same time, once they get licensed, we expect that as a university, we are going to actually do a pilot project of a solar PV plant within our institution, and also do awareness workshops within our community, just to make sure that we do actually the correct sizing of these solar components within our nation.
have the Shack-Hartman wavefront sensor, we have the deformable mirror, and the control software for this purpose, and that makes the first type of this.
Whatever is before you is Michelson interferometer, and one of the applications of Michelson interferometer is that it measures the thermal expansion coefficient. So in this case, you're going to measure the thermal expansion coefficient of an aluminium rod that's connected to a banana plug. So when you connect the rod, as you can see, we have a digital thermometer, and the wires are connected to the IC regulated power supply. So when the voltage is adjusted to like a certain voltage, probably 5 to like 10, you notice that there are some fringes that are going to be produced there. This is because an increase in the voltage is going to induce a temperature change here. The temperature change will lead
and control software for this purpose, and that makes the first type of this.
Whatever is before you is Michelson interferometer, and one of the applications of Michelson interferometer is that it measures the thermal expansion coefficient. So in this case, you're going to measure the thermal expansion coefficient of an aluminium rod that is connected to a banana plug. So when you connect the rod, as you can see, we have a digital thermometer, and the wires are connected to the IC regulated power supply. So when the voltage is adjusted to like a certain voltage, probably 5 to like 10.
Good morning.
You notice that there are some fringes that are going to be produced there. This is because an increase in the voltage
so I think
is going to induce a temperature
can start the next session.
change here. The temperature change will lead to an expansion of the rod. So when the rod expands, it's going to shift the mirror. The mirror, when it's shifted, you notice that there are going to be transition in the number of fringes.
Thank you. So we can start the next session. Our presenter is Professor Silvania Piera. She is a professor at the University of Delft. She studied a PhD in Brazil, a bachelor's and master's degree in Brazil, and proceeded to USA for a PhD. Her thesis was on the field of experimental quantum optics. She has over 3 years of postdoc experience, both in Germany and Netherlands. She is active in Photonics NIL, a national association for photonics and optics in Netherlands. Women in Photonics, Dutch Physics Society, Dutch Network of Women Professors, European Optical Society, and our current research interest is on optical metrology for particle detection and nanostructure characterization. So Professor Piera will be talking, or our topic of discussion is Fresnel and Vancouver diffraction. So kindly with a clap, help me welcome Professor Piera for the presentation.
Can you hear me? Yes? Okay. Okay. Today we are going to continue what we were doing 2 days ago, and I would like to just recall a little bit what we did yesterday, also in the practicum, because we basically looked at this diffraction pattern of one slit. Yeah? And the slit was very simple, just 2 pencils together, making a small gap. And you saw, if you don't believe in the mathematics, you saw also in real on the wall this kind of pattern. So this is the intensity as a function of the position in the wall, and there was a very bright spot in the center, and then surrounded by zeros, and then a small intensity on the 2 sides that get smaller and smaller. And then we saw the relation between the positions of these zeros, which had dependence on the width of the slit, and the wavelength of the light, and the distance that I was from the object. And then you saw also when I was squeezing the 2 pencils, so making the slit a little bit smaller, what happens to the diffraction pattern? Can somebody remember? Was like wider or was narrower when I make the slit narrower? Was wider? Yeah, it's because there is an inverse relation. So smaller the slit, the wider is the distribution in the wall. And that is it's a very important. You have to remember this whole lecture, because we are going to go back to that many times, okay? So remember that the smaller the slit, so means that the smaller your object, the wider you will be spreading the diffraction angles, okay? And then if you're projecting the wall, will be wider. Okay. So then we went to the formal theory of diffraction, which is considering any aperture, not only a slit, but can be anything. And then we propagated this light to a certain plane of observation, which in our case there was just the wall, the screen. And that we call Z. Yeah? So it's the distance between your object and where you observe. Yeah? Where you put your camera, where you put your screen or anything. And then there is a relation between, okay, so what I have is a contribution of a point P in a certain point P in the aperture, in another point P in the screen. And then we came up with this integral, which basically comes back to the idea from Huygens, which is sum of many point sources. So if I divide this aperture in small point sources and let each of these point sources propagate, making spherical waves and adding everything. So my question is that maybe you remember, why do I get, like some places I get no light, zero intensity? Why is that? Remember why? Because the first concept we talked about was the light was a wave, is a wave, right? So a wave has like some... Okay. So maybe I stay here. Yeah, sorry. So a wave, so has a wavelength and propagates. And what happens to different, maybe you don't hear anymore? You hear, okay. So what happens is light from one point and light from another point of an aperture travels a small difference in length. And this small difference makes that the waves don't add exactly in phase. In phase means that they add all in the same zero for this, the beginning, they add. So when they are shifted to each other, I can have a condition when I'm half of the wave that I have exactly zero, right? Remember that? So I summing everything, I can sum and get zero. Yeah, a sum of many things. If I make plus or minus, I get zero. So the whole diffraction pattern you see here is for each point is the contribution of all these points that contribute to that point. And then I go to the next point, I have to go to distribution of all these that contribute to that point. And another thing we talked about was that the center is symmetric in terms of the slit, the single slit, then I get a maximum. But if my aperture is arbitrary, then I may not get a maximum in center. Yeah, depends on how you get and how you illuminate also. But in any case, this integral is the full integral that is basically a sum of every point P1 within the aperture here, times some terms here, which had to do with these waves propagating with different distances. Now the R01 is the distance between here and this point. And this changes if I consider another point here going there. Okay? So this is a very complicated integral, but this is the full story that you need if you have an aperture where you don't know, you have a certain shape and you have a certain field coming in here, because it doesn't need to be uniform field. It can be also some light which is not uniform. So you multiply that by this aperture, and this is your aperture function here. And this is the waves that propagate with a certain distance, r01. This is a cosine term, which is usually is not so important if you're only talking about very small angles, so don't worry too much. And this is the integration within this full aperture, okay? So then we talked about making some approximations, yeah? Because these approximations can be interesting for practical problems. But the integral is valid anywhere. But I want to say, okay, what if I'm far away from my aperture? Or what if I'm not so far away from my aperture? What's the effect will be? Yeah? It's basically how you calculate R01. Because R01, it has to do with the z, which is this distance here. It has to do with xy. Yeah, so it's the coordinates of your point r xy, xyz, and in the aperture, and xyz in the screen. Yeah, the small x is in the screen, and is in the aperture. The big X and Y is in the aperture, and the small x and y is in the screen. So basically, if this is much bigger than the others, you can make some approximations. And that's what we do. So first well, this is just mathematics. I don't want to go very much to this. But you can write down R0 in terms of this, like just isolating the z outside and having these two terms here, which has a quadratic contribution here. And then you factor out some terms because they don't belong to this integral big X, big Y. And you are left with this part here. So basically, what I showed you that is this part here, which is ik divided by z, x, the small x times big X plus small y times big Y. This is a Fourier transform of this function here. So when I write the integral like this is the Fourier transform of this function. So what I have is what we saw last time is that the field at the screen is the field at your object or at your aperture, which includes the light field also, not only the shape of the aperture, multiplied by this term here, which is quadratic term with x quadrat squared plus y squared, and then do the Fourier transform of that. And nowadays we have an easy life because you can do this with the computer. Yeah. So there is what is called fast Fourier transform in MATLAB, in Python. You can calculate these diffraction patterns, and you can basically consider any type of aperture. Okay. So that is what's called the Fresnel approximation. Fresnel approximation means that you are not too far from the screen. So you are in an intermediate distance from the screen, okay? But then I can go even further and say, well, what if z is much, much bigger than this term here, for the maximum of this term? So it means that the whole diffraction is much smaller than the distance I'm considering, okay? And then you can do another approximation, because then the quadratic term, I can drop the quadratic term. So when you drop the quadratic term, we call Fraunhofer approximation. And that is, as I said, only valid if you are very far away. Because we have to remember, by doing this approximation, I'm considering that z is indeed much, much bigger than this one. You can also calculate the error. Okay, if I don't consider, how much will be the error I'll get, right? But remember that between the Fresnel and the Fraunhofer, there is the distance is very important from the object, okay? And this should be valid if I want to consider Fraunhofer approximation. The Fraunhofer approximation, of course, it's easier because now I have only the Fourier transform of my aperture function, which is just the field multiplied by the aperture. So if I want to do, now that I have this formula, let's say yesterday we were like about a meter away from the slit, and the slit is like maybe 50 micron. Yeah, so I had a good approximation of Fraunhofer. Yeah, it's a meter and 50 micron, small. So this could be a good approximation. So how we would calculate now the diffraction pattern? So what is a slit? A slit is like everything zero except from minus a divided by 2 to plus a divided by 2. Yeah? So just a small, like if the aperture is a. So all I have to, and only in one direction, yeah, because the y direction was free, only x direction that was being squeezed, right? And so actually I only have to do an integral in x, so I don't need the y term, and I do from the integral from minus a over 2 to plus a over 2, okay? And then you just do the integral. Yeah, you should know how to do integral, or you can do also calculate in the computer. But basically, this term here is easy to integrate because just exponential, you know what the integral of exponential is. And then do in the aperture minus a over 2 to plus a over 2. That's all you have to do for one slit. And then you get the same result that we got yesterday. We get also this sinc function square, which is this, which is this, if I square it, I get some distribution like that, okay, in x. Y will be just free, okay? So now you see that this is an integral, and I have to integrate, sorry, this one, still. It's an integral, and I have to integrate within the aperture. An integral, as I said, is a sum, right? It's a sum of things. The last time I showed that integral was a sum of point sources. So what happens if I put two slits together, one next to each other? How are you going to solve this problem? Can somebody tell me? So I have now two slits. So still one direction is constant, but in x I have two slits. How do I do this integral? Is it difficult? What do you think? Well, basically, I have to do is a sum of two integrals. One integral is the slit, the first slit, which is like from minus a over 2 to plus a over 2. And then the other slit is a over 2 plus the distance between the slits, and then from minus b over 2 to plus b over 2 for the second slit. So I basically do again the same integral. Just I change the initial parameters here. Okay? So basically it's a sum of two single slits. But what changes there? What do you think? Because I'm not going to get something which is just 2 times bigger than this. And why do you think you don't get that? I tell you, you don't. So what happened? Well, basically what happened is that when you go to this plot, so I see this is the first slit. So I always have to sum all the contributions in one point, right? That's what we learned in the first slide. So let's say that this one is the first slit. So all these contributions go to that point, okay? But then it comes the second slit. The second slit will be here, okay? Well, this second slit will have longer to get there, right? longer. So what happens in the second slit is that there will be, again, another shift in the phases. Okay? So I have to add all this and then also all this to that point, and always to this point, to get the entire contribution of everything. So what happens when you calculate everything is that you get this kind of pattern, which is the contribution of each single slit, but inside here, there will be some interference term. There will be something like a sinus, go up and down. And that depends on the distance between the slits. So it's a combination of an interference of two waves, which is just a sine, and the aperture function. Okay? So this is what you get. So if you don't believe me, you go home and make this integral, and you see that you get that. Okay? So you have to do this integral here, and just put the right limits here. You need two integrals, one for the first aperture, and the second for the second aperture. Okay? And then you see that. So what you see is like an interference pattern which has a global envelope, which is a sinc square function, but then modulated inside with like fringes. And the fringes depend on the distance between the two slits. So what do you think? If the slits get farther away from each other, will the fringes be more tight or more spread? What do you think? Just thinking of the concepts we talked about until now. Will be tighter, yeah. So the wider broader the distance is between the slits, the oscillation inside this envelope will be finer. Okay. So it depends if you want, depend on your application. Sometimes you want this kind of interference effect, so you can play with the distance of the slits. And the envelope is still determined by the width of the slit, the sinc function envelope. Okay, now let's go to another example. Let's say now I don't have a slit, but I have a square. A square. So how you would do that? Now your integral is 2D, right? It's not only x, because a square is x and y. So how you do that? So if the square is centered in 0, and is a of the side. Excuse me? You want to talk? Yeah, you can say. Yes. What will be the limits of your integral? No? No, it's okay. It's okay. Well, it's basically the limit of the integral of the slit in x and in y, right? Because it's the same. If I put two slits like this, I get a square. So basically, it's the sum of two slits, one in x and one in y. Okay? Not so difficult too. So what you get, if it's like that, I can separate. I can separate x and y because this is one I integrate only in x, the other one I only integrate in y. So what you get is a product of two sinc functions, one in x and one in y. So how will the diffraction pattern look like then? One is a sinc function x, the other one is a sinc function y. How is the diffraction pattern of one slit in x? It's like a line, it's like it spreads in this direction, right? So if the slit is like this, it spreads like this, right? In a central lobe and then like this. Well, if the other one is, if I rotate my slit, what do you think will happen? Yeah, it's like this. Oh, if I put the two together, I have a cross. Okay, because they are completely separable. So I have a diffraction pattern in x, in horizontal, and I have one in the vertical. in the center will be like something like a square. Okay? So that's how you deal with diffraction. So you are adding things. Okay? So sometimes if you have a complicated problem, sometimes you can make it simpler by thinking that is an addition. Okay? And also be careful where your aperture is. But basically, this is what is happening. Okay? Yeah, so that is the square apertures and slits. Very easy to do the calculation because just an exponential function to integrate. That's very easy. The only thing you have to think about are the limits. Okay, so think about if you have three slits, what do I do? This is exactly the same. Yeah, I take this slit, integrate from here to here, and then from here to here, and then from here to here, and so on. Well, if I keep increasing the slits, what happens? What do you think? What do I get? We saw yesterday. Many slits together, all the same distance to each other. It's a grating because I have like a light, no light, light, no light, light, no light. Yeah, they're all the same, periodic. So if I keep adding slits, I keep adding these. Start appearing some lobes outside, but they become big at a certain places, and then you see those points that we saw, right? So diffraction grating gives a center, and then one particular point here and one particular point there, and so on, and both sides, and always the same distance. And that you can see, that you can also calculate that. Yeah? So you can also calculate and you can see how the diffraction goes from one slit to many slits. Yeah? So if you have your program to do this, you can do one slit, 2, 3, 4, 5. You see what happened to so you see that more and more it becomes like a diffraction grating. So at some point you see just like one, and then nothing, and then another one, and then nothing, and so on. And that's what we saw yesterday, to a diffraction grating. A real diffraction grating would be infinity. Of course, infinity diffraction grating doesn't exist, so always you have a finite grating with some number of lines. But basically, it's the same integral. You just have to add infinite number of slits. Okay. Okay. So now this explains a lot what we saw in the practicum for a slit and the gratings. Yeah, the gratings, you also remember when the grating got smaller, the diffraction pattern, so the points spread more in the wall. And remember that because we are going to talk about that when we talk about imaging, will be important. But I would like also to go to a circular aperture. And why I want to treat a circular aperture is because in optics we see many things being bounded by a circle. Yeah? Circular apertures like a lens. Outside the lens, the light doesn't go to the other side. So if I send light to the lens, outside the lens doesn't contribute to what happens in the diffraction pattern outside the lens. So you have to bind the boundary is the lens diameter, right? But sometimes you have pinholes in optics. You use a lot this circular aperture. Well, how do I do this? Yeah, this becomes complicated. And the reason I want to show you this is just that to see how complicated it gets, even if you have a circular aperture. Yeah, because now you have, until now you have everything in X and Y, but a circular aperture will be one everywhere around this, if the circ function, so if this Q is smaller than the width of the aperture, and 0 everywhere else. Yeah? So it's something opening. So if I take a screen, I make a hole, yeah? A circular hole. Well, then I have to go to what is called a Fourier-Bessel function. This is all mathematics. I don't want to go too much to the details. I just want to show you, because this is not so easy to do. Okay, so you go to this, what is called the Fourier transform is the same, of course. The aperture, now here is the circular aperture, and I have to integrate to make this integration. But because x and y is not a good coordinate for circular symmetry, I can use cylindrical coordinates. It's easier. So cylindrical coordinates, you have a row and you have everything in cylindrical coordinates. And this is my aperture function here. So now you see that this part, that you can integrate first in theta. So if you write this whole thing here, you integrate first in theta. So you have, you integrate first in Q. And then you have that this integral here, 0 to pi of this, is called a Bessel function. And that is the first integral. And then you have to do the second integral, which is the aperture. But in this Bessel function, you have your aperture also there. So you have to take into account that. These are all like tabulated integrals. There is all analytical, so you don't need to do it yourself. You know that if this kind of integral has this solution, so you can use that. And so the Fourier transform is a circular symmetric function, and the aperture is circular symmetric, and the Fourier transform will be also circular symmetric. And then you substitute the G of Q, which now will be 1, except from 0 to W, which is the size of your aperture, right? The radius. And then you make the substitutions, and you get this integral, which is also quite complicated, but it gets another Bessel function. It's called the Bessel function of the first kind. So these are our results. Yeah, so if you do this integration using the cylindrical coordinates and using the properties of integration with Bessel functions, you get this as a result. So what you get when you have a circular aperture, so yesterday if we would have just a circular hole in a piece of paper and I shine the laser, look at the screen, you would get something which is the square, so this one. So the intensity would be, well, some constant here, but then the Bessel function divided by this term, and then squared. And the intensity looks like this. Well, you saw that before from, I think from Alessa. So you see it's circular symmetric now. Yeah, so it's not anymore a sinc function or lines or something. Now it's circular symmetric, and it's very strong in the center. And then there is surrounded by a zero. And then there is a small ring here with low intensity, again surrounded by a zero, and then another ring with even lower intensity surrounded by a zero, and so on. So you see this very center, which is very bright, but then zero, and then a small lobe, zero. It's the same as with the slit. And again, it's the same concept. Why do you get zero is the destructive interference at that circle, okay? So so that is what we get, and this is very important because this is also called in optics sometimes the Airy pattern. So if you have heard about the Airy pattern, is the modulus, is the square of the Bessel function, which is the solution of the circular aperture. And the important is this. And the important is that the D, which is the distance, the width of the central lobe, so going like the distance between the lobes until the first is zero, is given by 1.22 lambda z divided by W. And W was the size of the aperture. So you see that this D, as the aperture gets smaller, this D will be bigger. Yeah, same concept still as the slit. Yeah, the slit is smaller, diffraction pattern bigger, and Z is just the distance between the aperture plane and the observation plane. Okay, so that's a very important result that we are going to see later on. And, but for now, this is what you see. So you see, you have a light coming into a circular aperture. I'm consider the light being just uniform field. And then you have this airy pattern at a certain distance from the aperture, if it's far away from your aperture. So far, do you have any question? So what I'm showing you so far is that how we deal with this diffraction integral for several types of problems. So if you do any optics, you might be dealing with those problems. Apertures are always there. So you have many experiments where you put an aperture, or even your optical component makes an aperture for you. If your optical component is smaller than your beam, the optical component will make an aperture for you. So you have to be careful. So when you are doing experiments, never use a beam size which is as big as your optical element, because you're going to have very weird effects because of the aperture, diffraction effects. Okay, so this is what I wanted to say about the diffraction. So you can look in books. There are examples worked out with single slit, double slit, multiple slits, circular aperture, everything. One thing that complicates a bit more is this integral here, which is the Fresnel integral. Let's go back just to this one. Which this is the diffraction you have when you are not too far from the aperture. So if you are relatively close, you don't see those diffraction patterns we're talking about. Because you have to solve this integral, and this integral is much more complicated because it has this term there. Okay? So be careful when you are doing your experiment, whether you are really in the Fraunhofer regime, that you can use the approximation. Otherwise, you have to use this one, okay? Which is called the Fresnel approximation. But usually you have to be quite close to your aperture. Okay, so that's the circular aperture. And we come back to this later on. So remember those messages that I talk about now is that, okay, the width, if I have a grating, if I make it smaller and smaller, the diffraction pattern spreads more and more. And if I have more slits, I just add them in the integral. I just have to find the right integration boundaries. And then just solve the integral. If it becomes too complicated, you can solve with computer, okay? Like suppose that your aperture is a triangle. Then you don't want to start with trying to do by hand. Becomes too complicated, okay? But for example, if it's a cross, I can do it, you can. It's two squares, but with different dimensions. So all those things you can do, yeah? Okay. And now I would like to go to this, what's called this Rayleigh criterion, because it has to do with this minimum resolvable, because this is like, this is what is the diffraction pattern of a plane wave in an aperture, right? And an aperture is also like a lens. I don't know if you've ever seen, have you ever made a pinhole camera? Whoever made a pinhole camera? Yes. An aperture is a lens, I promise you. If you take a shoebox, make a small hole, and the other side you put a screen, like a transparent screen, and you go to a very dark room and you put this pinhole in to look at the trees outside, but your room should be very dark. You see the image of the tree on the screen. It's called a pinhole camera. Actually, the tree will be upside down, but you'll see just like if you would use a lens. So a lens and a pinhole, we can mix them because they do the same thing. But what happened is that I said that there is a plane wave coming into my pinhole, right? The plane wave, and I get this. Well, how do I get a plane wave? A plane wave actually is a point source in infinity Yeah, remember the first lecture? I said a point source, if you keep propagating, at some point the wavefront becomes flat. And you can think like really a star, the light coming from one star, it comes here as a plane wave because it's so far away. So if the star is like a point source, let's say, when it comes here, it's just like one plane wave. And but if I put that in my pinhole, so I want to make an image of my star, I get this. It depends on the size of my pinhole, okay? Of course, the wavelength, but that's a little bit more complicated. But let's say if I have a point source, I have to think a plane wave. There is a point source somewhere generating this plane wave, okay? And this is infinitely far away. Of course, in the lab, you can make approximately plane wave, but here we are talking the perfect plane wave. But so this is the size of your spot, which is actually originally generated by one point source. A point source should be infinitely small, but you see that this is not infinitely small. Yeah, it's like 10 to minus 4 here. So in meters, it's not infinitely small. Yeah? It has some dimension. It could be a micron, 2 micron, whatever, but it's not zero, not like very small. And that makes this come to the Rayleigh criterion. So the Rayleigh criterion means that if I have two stars very close by, and I let them come to my optical system, let's say that the two stars are not interfering, so they will make 2 point source, 1 point source here and 1 point source there. And there is some separation between the 2 point sources. Yeah? And because they are not in the same place, they are in two different places. Of course, the image will be also in two different places. And let's say one is on axis, and the other one will be off axis, let's say. But what means that this Rayleigh criterion is that if I have 2 point sources, because we have this dimension here, which is not zero, I have to add those two waves together. And when I add them, depending on the distance, if they are far away apart, they will have a lobby here and one lobby there. Then I can resolve both. But if they start coming together, they start adding together here somewhere. That here there will be not a real separation between the two. And if they come even closer, I cannot distinguish them anymore. So I cannot tell is that one or 2 point sources or 2 stars coming in my telescope or something, okay? And that is, again, this lambda that they said the minimum is when this one is in the zero of the first one. And then this is the minimum, 0.61 lambda z divided by w. W is, again, the aperture of my, the size of my aperture, my circular aperture. So that's where this Rayleigh criterion comes from. The diffraction of just a circular aperture. Okay? And this has a lot of implications in optics, in imaging, because that means that I cannot image, if I image in this way, I cannot image anything better than when they come together. When they come together, if they come more close together, I cannot say how close they are, if they are 2 or 1. I have no information anymore. Okay? And this is a very simple image of two sources, but of course an object is much more complicated, so this contribution will affect the entire image. So what I can say is that, okay, smaller than this distance, I cannot resolve entirely my object. Okay? So what can you do to improve? You have to widen the aperture, because that's why they make big telescopes. Why the telescopes are huge? Because the wider the aperture, more information from your stars coming in, your point spread function narrows down. And then with this way, I can make a better image of the stars. So now you see these huge telescopes, yeah? And there's even more. They have combination of several telescopes. All those kind of techniques is because they want to improve how you see the stars in the sky. These are images that is really limited by this resolution limit. Okay? Okay, now we go to lenses. Sorry, the drawings are a bit light, but a lens. Okay, a lens. What is a lens then? A lens is a device that, if I come again with this plane wave, all these plane waves becomes like some sort of spherical waves that converge to a point. Yeah, do you know that? So maybe when you were a kid, you had this magnifier. I had a magnifier, and I just put in the sun, and you get the sun concentrated in one point. Yeah, so the sun is my plane wave, and the magnifier made all the light concentrate to one point. And it was very powerful. I could burn leaves with that very tight spot that I make with the magnifier. So that's what. So actually, the lens is a transformation of the wavefront. So the wavefront of the light is like a plane wave before, let's say. So it will make a spherical wave, converging to a point. Okay. So that's all that a lens do. So actually, a lens can be seen mathematically by some transmission function, which creates this like some sort of a spherical wave converging, a converging spherical wave, which mathematically can be written like this. And this F here is the focal length of the lens. So if I have a plane wave coming in, what is F? F is the distance between the lens and where I get this concentrated light point. This is the focal length of the lens. To make that real, you have to polish two surfaces with R1 and R2. R1 and R2 can be the same, but basically to get this F, the value of F, it depends on the radius of curvature of the first surface and the radius of curvature of the second surface. And this is the index of refraction of the glass, the glass that you make the lens. So, so that's F. So I have to put F here because how it converges. A longer F, this will converge in a longer, so of course the curvature will be different when it goes out of the lens. So basically what happens is that the plane wave comes in, and right after the lens I have already a spherical wave. Okay? And then it goes to a certain, propagates to a certain distance. So this is how we model a lens. And a lens also has a finite size. That's very important. We don't have infinite big lenses. Lenses are finite. So it means that this curvature, because we are talking about diffraction, and I told you, diffraction, every aperture affects the field that goes after this aperture. So here I have diffraction means that inside this lens, I have this spherical wave transformation, but outside the lens, I make it zero, because it will be my holder, and the light will not go around the lens, it will go just inside the lens, let's say. So I have a lens aperture. Inside the lens is a pupil, which is 1 here, so only the phase is being transformed, and 0 everywhere else. Okay? So now how do I deal with the diffraction integral with this now? Because again, I have an aperture now. Now my aperture has a lens in it. So how do I do that? Do I have to do anything else than consider this as my pupil function? Okay, the answer is that you don't need to do anything. Your pupil function will be just after the lens, will be this aperture, which is just like a rounding surrounding the lens, so a circular aperture surrounding the lens, plus this function, which is this phase function, which is generated by the lens, right? So basically, what I have, if I go back to my Fresnel Fresnel equation that I had before. I'm using Fresnel now because now we are talking about a small distance, not Fraunhofer, which is meters away, Fresnel. And then you propagate that at distance f. So in our case, we had the distance z, which was the object and my screen. Now I just propagate to the focal point because I want to know the diffraction pattern at the focal point, right? Yeah, so then you put that in the integral. So this one is now the composition of my pupil function, which is the aperture times the phase that is introduced by the lens here. But then, you see this one has a e to the minus ik divided by 2f, and this is e to the plus ik divided by 2f. So when I can eliminate this term, and I only get the p, which is the circular aperture again, and this term, which is just again the Fourier transform. And then there is again this these phase terms which were there again, but when I take the modulus square, these phase terms disappear, or they just become constants. And you see now, this is again the Fourier pattern of the input pupil, now which is just the circular aperture, because the phase transformation of the lens has been eliminated by the Fresnel term. Well, that's what is nice. That's why I say that lenses and circular aperture are similar. So, yeah, so in this way, yeah, I can now calculate how the focused field is. Yeah, the focus, well, it doesn't change anything. No, you get the same type of focus. You also get this Bessel function. Yeah, you also get something like this. It's just that now you're going to have different units here. Yeah, because now you have to calculate in these units, which depends on the focal length. You see, depends on the focal length, it depends on lambda. Oh, depends on lambda. That's also something interesting. Yeah? Because what happens is if I have a shorter lambda, my point spread function also will be smaller. So that's also interesting to see. So now you know, okay, you know propagating light from one place to the other place, I use the diffraction integral. When I have a blockade in my field, I have to add this pupil function, yeah, and still go propagate with the diffraction integral. So now we have to go to more complicated but a very important thing in optics, but maybe you do that every day. Yeah? Like your camera, when you take a picture, you're making an image. Yeah, with your camera. Your camera has a lens, yeah, so it has an object, the tree, and I see my picture, yeah, in my phone. So basically, there is an optics step between what is registered in your CCD and the image you want to do. Is the lens, yeah, and that can be very complicated, like Alessa showed yesterday. It can be objective with many lenses. But even one simple lens, I can make an image. So how do I deal with this now, this problem? Well, this half a problem we already did, right? We already know what happens when the light passes, whatever light comes in here, passes through the lens, gets this phase profile, and then propagates to a certain distance, like here Z1, Z2, let's say, to a screen or where I look at my image. It can be also the CCD camera or whatever, film or your eyes. Our eyes, we also have a lens in our eyes, so otherwise we would not make images. So everything, basic thing of image formation is one lens, object, image, and there is a relation between object and lens, the properties of the lens and the image. Actually, from geometrical optics, we can predict where will be the image plane if I know the properties of my lens and if I know the distance between the object and the lens. You know this geometrical optics formula. So we will see this geometrical formula soon. But the idea is that if I put my object at a certain distance, z1 of the lens, and my lens has a certain focal length f, there will be one plane where the image will be formed. And there is a relation between z2, z1, and f. Okay? And that is, we can also do that using this whole theory I'm talking about now. And I come back to that problem. Why do you want to kill an ant with a machine gun if I can use geometrical optics? Because what do you learn from geometrical optics when you do an image? The only thing you can do with geometrical optics is predict, okay, if I have an object here, and if I have this transfer function here, I can predict where the image is and the magnification of the image. But I don't take into account this point spread function that we are talking about. I'm not taking account this. Because in geometrical optics, a ray is infinitely small, and a focus is one point. It's mathematical. But in the reality, it does not happen that. So the geometrical optics would be making just the image formation geometrical optics would be just a perfect replica of my object. There are some things you can do with geometrical optics. For example, if your lens is not perfect, and you know how imperfect this is, and then how the rays will change, then you can calculate what would be the image there. But further than that, you cannot do, because you are not considering the wave properties of the light. You're not considering diffraction. So you're not going to hit the diffraction limit with geometrical optics. But we do in the lab. We do in our real life, because light is a wave. Geometrical optics is just an approximation to make some problems easy. So if your goal is only to know where the image will be formed and how big the image will be, if I know my distance is here, then you can use geometrical optics. Very simple formula. I say my image will be like 1 meter from the lens, and it will be a magnification 4. Then I have it. No problem. But if I want to know how the image will look like, the details of the image compared to the object, geometrical optics is not going to give that. So what I have to do is to go through this whole diffraction theory to calculate what will be the predicted image, given a certain object, given a certain lens. Okay? So then you consider this like H function, which is called the impulse function, as the field produced at xy, which is here, by a unit amplitude point source here. So we are actually now creating a new plane. So in the first lecture, we had a plane here with a point source here. We are looking at diffraction here, right? Now we are creating a new plane, which is where my object is. And let's suppose my object is one point source, which is like one star in the sky, let's say. This is my object. So 1 point source. So I want to know how it will be if I take this object and put in a lens, how it will look like in this plane, given a certain size of the lens, given a focal length, and given the distances. Everything is important. The distance is also important. Okay. So first what we do is to calculate the field at here. So this is the input field, so UI, which is, again, is the same thing we are talking about. So it will be this impulse function multiplied by the function of my object, which now is only 1 point. 1 point source at a certain point in the somewhere here. So this is the field that I have here. So you know where I'm going. Yeah? So if I know the field here, then I do the same process I was doing before. So first I want to know what is the field here after this propagation here from the object to the lens. Okay? So again, the field at the lens is a divergent spherical wave. Yeah, because this was a point source, right? This was a point source, so this becomes a spherical wave. And if now the distances are not infinity, let's say, if the distance is finite, it will be still a spherical wave. And I cannot approximate to a plane wave. Let's make the general solution. Then you can simplify if you want. But so you have a propagation Z1, which is the propagation between object and the lens. And and then you have a paraxial approximation, so you neglect some terms, make this cosine term small. So after the lens, what I have this one, which the field just after the lens, and the pupil function now. Yeah, because I need the pupil function. Why? Why do I need the pupil function? Because I said that the lens is blocking the rest. Yeah. So even if this spherical wave is very big when it comes here, will be clipped by the lens. Because only this part of the object, the spherical wave from the object will contribute to the image. Everything that's outside does not contribute to the image. And this is very important, very, very important. So remember that, because later on you'll know what I mean. So you have the field after the lens, and then you go to propagate this field at a certain distance, Z2. So I have the field after the lens, propagated difference Z2. So then I know my impulse function at the screen, which will be this field here of the pupil, this Fourier transform part which has these squares, and the integration that we are used to until now. So now you plug in what is this, which was the pupil function 0 and 1, 1 inside the aperture, 0 outside the aperture, and those terms which was the propagation, the Z1 and Z2, because they come together. This is Z2, the other one had the Z1 here, remember? You had a Z1 here. So you propagate from object to lens Z1, from lens to the image Z2. So you have these two. And you have F, because F came from the lens. 1 over F came from the transformation of the lens. But now you see, before when I had my plane wave and I was looking at the focus, I could eliminate the quadratic term, right? And now you see that this quadratic term is multiplied by this function here. And look what this function is. Is it familiar to anything that you have seen? It's 1 divided by Z1, so distance between object and lens, plus 1 divided by Z2, distance from lens to image, minus 1 divided by F. What's that? Back to geometrical optics. What's that? Nobody ever seen this? Yes.
If I understood you, since we started, if I understand your question, you're asking what is 1 over F?
Now, what is this whole term? 1 divided by Z1, but 1 divided by Z2 minus 1 over F.
That is simply the old lens equation, 1 over F is equal to 1 over V plus 1 over U.
Yes, yes. Which means is the equation that we use from geometrical optics to find out where your image plane is. Because you have Z1, you have F, you have Z2. So if you want to know Z2 is equal to, so you have to go back here. Oh, sorry. If I want to know the position of my, oops. If I want to know the position of Z2, I have to say 1 Z2 equals to 1 over F minus 1 divided by Z1. Yeah? Yeah, so this is just the geometrical optics prediction, or where the image should be. And what we come up in this complicated integral is that if I make this equals to 0, because it means if E1 divided by Z2 plus 1 divided by Z1 equals to 1 over F, which the image quantity, this is 0, right? So I can eliminate this term again in a different way. The other one was just a plane wave. So it means that, but it's not strange that it's like that, because a plane wave would be the object in infinity. Or if it's infinity, 1 divided by Z1 would be 0, right? So what I would have is that 1 divided by Z2 equals to 1 over F. So Z2 equals to F. So if the field is a plane wave, and I put a lens, I have the distance F, where the point source is. But if it's not a plane wave, because it's generated by an object which is in a certain distance from the lens, I have to obey this equation to make this term be 0. And that's what we call, in the Fourier optics, the image condition. It's the same. It's the same as the predicted geometrical optics image condition. Well, now life is easy again, because if I make this thing 0, I go back to the same integral that I had. Yeah, so I can write down in terms of magnification now, because you want to know how big your object will be, which is Z2 divided by Z1. So if I put everything in terms of Z2 plus divided by Z1, put a minus because the image is inverted, you get a magnification, right? So I can write like this now. So what I see is, I get a Fourier transform. That's why it's called Fourier optics. So this is the pupil function. And this is the Fourier transform of the pupil function again. But then as these terms here, yeah, so there is a center in these coordinates here, which is where this point will be formed. And that has to do, of course, with the fact, let's go back here, that if I have a point here, you know that this point is imaged there, right? So this displacement that you see. Okay? So I did everything following completely the diffraction integrals, and you get to the image formation. But what is nice about this is that now I really get an image that is the same image I will get if I put a CCD, take an object, illuminate, put a CCD camera, and look at the object. This is what you get, because this impulse function here is telling you what is diffraction doing to the details that I have in my object, and what the diffraction is doing in terms of transferring the details, so the small details of the object to the image. And you can see that you can play with this. You can play with many things. So how can I make better images? I can play with the focal length. I can make it short. I can play with the aperture. I can make it large. I can play with the wavelength, because the smaller wavelength, the better will be the image. So all these things I can play, and then to create better images. But this is the most fundamental way to really calculate what to really see it. So if you ever make an image system and you don't see very well what you wanted to see, you have to go back to this equation. Where is it wrong? Why I don't see certain details of my image? Okay, later on I will show you how you really look at that. How much time do I have? Or is already past? 10 minutes. So maybe we stop here, because then I go to other things. So questions? Yes?
Allow me to take you back a little.
Mm-hmm.
That is that plot for the point spread function. That
the circular aperture?
Single slit, yeah.
Yes.
That one. Help me understand the D. Where do we stop? The D equal 1.22 lambda Z over W. So that D, the width of the central lobe,
Yeah, is the distance between the zeros in the central lobe of the Bessel function.
Okay.
Yes.
And then the UI. Oh, before we go there, there was the transmission function.
UI was for the lens, right?
Before we go there, let us go to
that's UI.
Yeah.
Here.
And I'm saying, before I ask here, I want to know, there's something little I want to know about the transmission function, the T, the transmission function, the T as a function of X and Y.
Yeah.
Now, just put in physical terms, what does the transmission function signify?
Yeah, the transmission function is the function that you have to consider when you do this diffraction integral. Because as I said, when we just, let me see the diffraction integral. Let's go back to the diffraction integral. Yeah, this one, let's say. Yeah, this one here. So when we're doing only slits and I come in with only like a uniform field, like a plane wave. So a plane wave is 1, so it doesn't matter. Yeah, so then I only have the U is just the aperture function. So that from minus A over 2 to plus A over 2 is 1 and 0 everywhere else. Okay, so that's the aperture function. But this is a general aperture function because is what you find in the aperture plane times the field that comes to the aperture plane. Okay, because if I have a uniform is 1, but I may not have a uniform field. For example, if I have a finite diverging wave, is 1, but the phase is not flat. So I have to add in this U the phase. So it depends on the light and the aperture. Okay, so otherwise that's the full aperture function. That's what you have to plug in there. Yeah, it's clear?
Yeah. And then finally, just been excited with the final equation, the UF. It's so versatile, and it can see several things that typically you will not see in geometrical objects. Thank you for that.
Yes. Any other question? Don't be shy if you wonder something you don't have me. Just ask something you maybe didn't understand. Might be too much for you for this run. Of course, you should digest a little bit of these concepts. But I hope I showed you, like starting from the simple slit problem, that you can go all the way to this, and then you can get really the predicted image of your system. Yes?
Yeah. Thank you for this elaborate discussion on diffraction. Now, there is that equation where you are setting that 1 over Z1 plus 1 over Z2 minus 1 over F.
Yes.
You set it to 0.
Yeah. I set it because this is the condition for imaging in the geometrical optics. And if I want to make an image, if I make this 0, I am in the same plane I would have imaging in geometrical optics. Where was it? Here, this one. So if I make this 0, it means that 1 divided by Z1 plus 1 divided by Z2 equals to 1 over F. And that's the plane that makes an image in geometrical optics.
In other words, you are setting the object at F.
No, I'm setting
the image at infinity.
No, I'm setting the object at Z1 from the lens, and I'm setting my screen Z2 from the lens. So, but I don't know the Z2. I'm free of where Z2 would be, right? But only one value of Z2 if this one is fixed and the F is fixed, there's only one value of Z2 that gives the image. Otherwise, here or there will be blurred.
But for that condition to be 0,
yeah,
it means that 1 over Z1 must be equal to 1 over F
minus
so
1
that
over
1 over Z2, you said Z2 to infinity, right?
No. Z2, maybe I was confused because of the stars, but here is a real problem that I have in my desk. Let's say I have an object, I have a lens, and then I illuminate the object, and I look for the image plane with a screen, okay? But you know from geometrical optics that depending, if I fix the position of the lens and the object, and if I know the focal length of the lens, the position of the image will be only one place, a certain Z2 that fulfills this equation. It fulfills this equation, this one. You can try in the lab. You can put an object, put a lens in some distance, and look for the image plane. And you see that this condition will be satisfied. And if I am farther or closer than this condition, I get a blurred image. I only get a good image when I am in the condition. Yes? Yes. Don't ask too difficult questions. I'm still younger than you.
Yes. Sylvania, there's a possibility to describe diffraction in Wigner space, in phase space, with Wigner functions. Did you ever found this helpful? Have you ever been using this?
No. I have seen that the people use, but I never did myself, no. Okay. But what would be an interesting application in your?
No, so basically it's a united description of the both conjugate variables, the position and the k, the x's and the k's. And then, like Fresnel diffraction is then associated with fractional Fourier transform, and
okay, yes.
So I think it's kind of mathematically, it's kind of nice. Everything is in one. But of course, I'm not sure you can apply this to. I'm not sure what happens when you have lenses and do imaging. Maybe then it's not so appropriate. But when you look at just that reflection in free space, I think it's a very nice way to do this. And I'm asking because I was wondering whether it has been useful in real practical applications.
Yeah, I've seen papers, but I cannot think of a real application on this. But I can imagine that in some fields where they need to record the diffraction pattern quite fast, and they need some model that could help. For example, adaptive optics or so. But I heard about, but not in applications for imaging. Yeah.
Thanks.
Yeah. Any other? Okay. Can I have a little bit of water? Some water. So I can start now the second. Now I have 50 minutes, okay. Can you open for me? It's too hard. Thank you.
Some more questions?
No questions? Okay, now I'm going to introduce some concepts that is used by both industry and maybe by you if you want to see how good I can make an image. Okay, how good can I make an image? Because unfortunately, life is not so easy. Yeah, we know about that for other reasons, but we are assuming that this lens is making a nice phase profile, right? Which is given by this nice function. But do you think that in real life we can achieve that? Yes, but not so simple. Yeah, so it's not so simple. You can get really imaging systems that are very close to the what we call the diffraction limit. So the best you can do, considering that we have diffraction, but sometimes there are some problems. Yeah, so like Alessa was saying, yeah, you need an objective, you need many lenses to make a perfect diffraction limit spot. And maybe if I use one lens, it's not good enough. So, when you make many lenses together, you may have a small misalignment, you may have a small angle between the lenses, or maybe the distance between the lenses are not good. So there are many fabrication problems that can affect the quality of your image. Yeah? So to achieve the diffraction limited the image is not so easy. It's possible nowadays because there are very good components that you can buy. But again, you have to think about how that is not so easy to get. If I just get a lens off the shelf from Tor Labs and I'm not going to get the best image I can. But sometimes you want to know how good it is, and is that good enough for what I need? Yeah? So you have to find somewhere a way to qualify the lens, qualify your image system. Okay? So if I go back, so what we call, this is the frequency response for the diffraction limit coherent image. Very, very complicated title, but basically you have this Fourier transform that you know already. And I can write the Fourier transform in terms of x and f of x, but f of x I defined here before. Where was that? Here. F of x is the x coordinate, which is the coordinate in my screen, the x and y coordinates of my screen, divided by lambda f. Okay, this is my fx. And so you see that there is units of 1 divided by length, 1 divided by meter or so. And that we call spatial frequency. So it's like frequency, the space is x, the spatial frequency is 1 divided by meter. So when you do the Fourier transform, you have Fourier transform between the coordinates x and ffs. So when you do the Fourier transform in x, you get ffx. So this is what is here in this. And ffx actually is related to the spreading of your diffraction waves. So when I had this single slit, the spreading, so the angle that I get this zero, it was an angle, right? Because if I put my screen further, this angle changes. So it's related to this angle. Of course, if I put a screen, I have a certain position in x on the screen, which I project the angle in this position. So basically, what you have, what we call the amplitude transfer function or modulation transfer function, you can see that also in the literature, is basically the Fourier transform of that impulse function. Impulse function was that if I had a point source, a lens, I wanted to know what I see in the screen, right? That's the impulse function. So what happens if I have a perfect image of a point source? Is what I see in the screen. And it depends, so it's the Fourier transform of this point source, let's say, which is there and here. So actually, because of this property, you remember that this was also the Fourier transform of the pupil function. So basically, the amplitude transfer function is the Fourier transform of the pupil function, but evaluated in these units here. But that's all. The only change is the unity, but it's the Fourier transform of the input function. The pupil function, what is in the pupil. So if you remember, for the point source, the point source is like was this spherical wave, but was bordered by my circular aperture, right? Because everything outside the circular aperture was 0. And then I went to going on for doing the image on the other side. So this amplitude function is just the circular pupil. So the MTF is very easy. It's 1 everywhere, and a 0 outside the circle. Okay? So what does it mean? What it means that these frequencies here, these frequencies fx and fy, they are bounded by being inside here. Everything that's outside does not go to the image, does not contribute to the image. And I'll go back to what we saw yesterday. Yeah? So let's say we had the grating. Do you remember how the points of the grating look like? So I had like a meter away. And how was the points? They were going where? Did they fit in the screen? They did fit in that small screen, right? Where are they? They were going all the way to the whole land, right? So I had like several orders of the grating going everywhere, right? And what happens if the grating gets smaller? It spreads even more, right? And here you start seeing what is the importance of the lens that I use and how I transfer the information about the grating to the image. Because suppose that I have a lens, and I had my setup yesterday like this, so I put a grating, I had a point in the middle, and I have like the first orders on the sides, let's say 5 centimeters or so away, and the second another 5 centimeters and so on, right? So suppose I have a lens that only sees the 0 order, and I focus that, right? Suppose I have a lens that's small enough, only look at the 0 order. What kind of image? Do I see the grating? Do I image the grating? What do you think? If I go to the image condition and everything, can I image any grating there? If I only look at the 0 order? The answer is no. You don't see any grating, because 0 order has no information about the grating. 0 order is the same as if I had a piece of glass there. No object at all. Then I can make a bigger lens and take the 0 order plus and minus first order. Okay? Plus and minus first order only. Then I make an image. So what do you think you see? Do you see the grating? Maybe because you have a small like let's say a small contribution of the grating in that points that were adjacent to the center. But there are many more, right? There are like infinite number of points. I only get in the first one. So what you see a little undulation in the image. You don't see the grating. You see a little undulation only, because there is not enough information, only a little bit information. Then I make a bigger lens, and I take 2 orders, 2 orders. Then you will see that my image will get better. You'll get more like something like a sinus or so. And if I make a huge lens, which will be as big as a like 2-meter lens that take like 10 orders or so, then the image will start getting close to the image to the real object. And that means that each component of the diffraction order is important, it contributes to the image. And my image is formed by the collection of all those points. If I block them somewhere, I'm limiting the resolution of my image. And that's how the numerical aperture that was talked about yesterday comes from. So instead of making a big lens, I could think about a lens with a short focal length and bring my lens very close to my object. That's what they do in microscopy. They make as short as possible because you go very close to the object, and then those diffraction orders are still not too far away. They are still close by. So I catch more orders in a smaller space. But the amount of orders I catch, I make my image better and better. So this function tells you that everything, so if I have everything that's inside this circle, so all the frequencies, the angles that come to my lens will contribute to the image. Everything else will not contribute because I'm putting 0 to all of them. So this is what is called the modulation transfer function. So if I keep the lens the same and I change the grating, I can change to a smaller grating. That means that I will lose the resolution with the same lens because this grating will diffract at higher angles and then again will not hit my lens. And again, I lose the resolution. And if I keep decreasing the size of the lens, the grating, the period of the grating, at some point, I don't image any grating anymore because nothing has passed to the lens because the first order is outside this circle. Okay, so determine the circle depends on the F, it depends on the aperture of the lens. So, and then the spatial frequencies that come from the object. How are they spread? Okay? So the more details of the object, the less will pass to this, because this is a hard border. I only pass if I belong to these frequencies here. Okay? You can also try this in the lab, because you can change the aperture size, and you see how your image gets worse. If I make aperture smaller and smaller, same lens, same object, same screen, the image gets worse, because I get less information about the object going through my image system. So this is called is the coherent imaging. And then there is the incoherent imaging. The incoherent imaging, of course, is more popular because it's the imaging you do with light sources like the sun or like those light bulbs here, these kind of things. So just what you do in photography or all types of general imaging. It's a little bit different. Now is called the optical transfer function, OTF. And that is actually the Fourier transform of the modulus square of the impulse function. And that's why, because the coherent imaging, you don't add the fields, but you add the intensities of each contribution. But it's again defined in the same way. So you take the modulus square of your impulse function, take the Fourier transform. This is just a normalization. So if you just normalize the h, just to get 1 when is in the 0, and then you get your optical transfer function. And the optical transfer function from you can relate the optical transfer function with the modulation transfer function. This you need to use some convolution properties of the Fourier transform, but basically what you get is an autocorrelation of the MTF. The OTF is the autocorrelation function of the MTF. And it can be expressed in this integral. It's a little bit complicated, but that's the relation between the two. But if you want to just the definitions, one is the modulation transfer function is the Fourier transform of the impulse response, and the optical transfer function is the Fourier transform of the modulus square of the impulse response. And what you get is that, visually, the autocorrelation means that I move the pupil around, and then you get the overlap between the two pupils. So when they are completely together is 1, and that goes to 0 when they don't touch each other anymore. And this area is this solution for this integral for all points. So what you get as the optical transfer function for a circular aperture is something like this, something like a cone or so. But what is important in this, so these are all definitions you can calculate, because if you have the impulse function, you can calculate that. It's not easy integrals, usually we do with a computer. But basically what it says here is a little bit different from the coherent transfer function, is that in the low frequencies, that means the light with the object that has big dimensions transfer very well, and as the dimension of the object becomes small, it transfers less. So that's why you get not so good image, because the high frequencies don't image very well anymore. And that, of course, finally has to do with the diffraction limit. But this is a way to visualize how good every component of your object will be transferred to the image in terms of details. So if I have a detail in my object, I want to know how good it will show up in my film or in my camera. Okay? So that's a very useful thing. Why do I introduce this? Because it's very useful. Because suppose you build an imaging system in the lab. You use real lenses, real distances, real objects, all kinds of things. So nothing is like very nicely mathematical. But you want to know how good these frequencies will transfer to my image. So what you do is that you use it's called a resolution target. A resolution target is a plate that you buy, and they are calibrated by metrology institutes. And they have like 3 lines, so 3 lines separated like this, and these lines become smaller and smaller. So they start big and become smaller and smaller. I mean, the distance between these 3 lines. And they go really to very, very small thin lines and very, very small spacing. So what you do is that you make an image of your object, of this object with all those gratings, and you look at the visibility of the 3 lines. Because if you can resolve it very well, you will see an image of the 3 lines, right? You'll see like constant, 0, and so on. But as the lines are becoming smaller and smaller, closer to each other, you don't have this anymore, but you start having this transfer function which is degrading as the gratings are getting smaller and smaller. So actually what you do is you make this plot of all those frequencies. So you calibrate this axis here being the periods of your grating, of your of this three line components. Because in the box that you buy, the 3 lines are there. What's the frequency? And you see, and you normalize to 1, with the biggest grating where you can do very well, 0. And then you see the degradation, and you compare to the real theoretical one. I bet you get worse than this one, or as good, but never better, because this is the best you can do in an incoherent system. Okay, so what you have is that sometimes you have something that goes down a little bit here or something, or sometimes really goes down like that. That means that your imaging system is not performing well. And then you know that some of those details of the object is not going to be imaged very well. Okay? So these are things, and there are tricks that I'll talk about that next time, that you can manipulate this, but this is the real thing, is if I have the whole aperture open, and I let all the spatial frequencies pass. And again, we'll get to 0 at some point, yeah? So all frequencies that are bigger than this one all details that are smaller in the object, that's not going to pass this frequency. And this is the diffraction limit, basically. Okay? So this is what is called the OTF. So this you can find sometimes when you buy an imaging, some lens or something, they give you this OTF. Because that's what's the quality of your lens. Yeah? So that is the 5 minutes? 10 minutes. Okay, thank you. Okay? So this is, MTF is for coherent systems. OTF for incoherent systems. They are a bit different, and you see that OTF is, MTF is a hard, it means that all frequencies, all details pass with the same quality, let's say, but then at some point it goes to 0. And the OTF, depending on how many details you have, the curve goes down slowly, so it means that the high frequencies do not show up very well in the image. So the small details are not so nice there. And you can see that in a microscope. So a microscope usually has different objectives. I don't know if you ever looked at a microscope. So the first objective, you don't see good details, and then you go to higher numeric aperture, means the aperture is larger or the focal length is shorter, so I get more spatial frequencies from the object, then I make a more sharper object. But at some point, there are some details that I don't see very well. And that means when you are getting to this area here of the point spread, the modulation transfer function. So it's useful if you are really caring about your image, how good your image is. It's useful to make this measurement. It's not so difficult. You take just a picture of this target and make the measurement and make the visibilities and plot. That's all you have to do. Then you know how your system is performing. I tell you, to get it really perfect is very difficult. But then I would like to talk about aberrations, because aberrations, they do exist, and most of the lenses have aberrations. But sometimes you get aberrations from the environment where you are. Yeah, so because you are assuming now that nothing happens between the lens and the object, and the lens and the screen, but I can have disturbances of the air, I can have lots of other problems. So it means that my pupil function now will be the normal pupil function I had before, let's say the pupil function of the lens or the aperture, multiplied by this. And this describes aberration. So it's a phase term. So like e to the a, k, and w. W is called aberration function. An aberration function, like if I have my circle here from the spherical wave from the lens, means that something happens that distorts this circle and can be anything, right? But if I can describe that is just a deviation from what would be the perfect sphere. So this is called this omega here, the aberration function. So now what you have to do is to just multiply that, because it's the same thing. I always consider what's my pupil function is what is in the pupil. So is the field coming in, is the lens, and is the aberration introduced by the lens, or maybe the field before came in the lens, whatever. But it can be described by this term here. And that is all. That's how you do aberration. Yeah, so you have to put this one here, and calculate your optical transfer function now with this term. Okay? And it becomes complicated, of course. You can write in polar coordinates. Usually they are in radial coordinates, and because lenses are usually like circular geometry. Not all aberrations are circular, but most of them are, if they come from lenses. So you don't need to do this, but usually it's done like this. And can be represented by Zernike polynomials, And Zernike polynomials is like are polynomials that are common, like aberrations that are commonly found in optical systems. And so if you have a chromatic aberration, a spherical aberration, a coma, or cylindrical aberrations, everything you can describe in terms of Zernike polynomials. So actually, you can expand your function, aberration function, by a series of Zernike polynomials with a certain coefficient. And depending on the coefficient is a certain type of aberration. So now, well, I don't want to go to the whole thing. It's quite complicated, but these are those Zernike polynomials, the radial polynomials and the circular ones. And they are listed. These are the aberration, the Z. So these are the aberration coefficients for all types of aberration, coma, astigmatism, tilt, field curvature, everything. So these are the common aberrations. So if you know, okay, you have a certain aberration in your system, you can just add this term and calculate your optical transfer function. These are the aberrations, how they look like, and at the pupil. So these are what happens to the phase of the light when it's in the, so this would be the perfect one, and these will be the different types of aberrations you commonly find. And finally, you see here, you cannot see very well, but what's the effect of a certain aberration in the image? So you see, if you have a coma, your letter E will be different. So if you have this kind of a spherical aberration, you have this. If you have a quadrifoil, you have this. So you can calculate how your image will look like depending on the aberration function you have. And you can also calculate the optical transfer function with the aberration function that you have. So if you have a certain optical transfer function, you can go back to see which are the coefficients giving the aberration. So you can go because all mathematically described. So you can do that in both ways. So find out what are my aberrations given my transfer function, or if I know the aberrations, I predict the transfer function. And once I have the transfer function, I predict the image. So that's how the kind of things you can do. And I think this is the last slide. So we start with the propagation of light, just with a very simple slit. We look at the diffraction, Fresnel and Fraunhofer, image information, and optical and amplitude transfer functions, and aberrations. I suggest those books if you want to go for more in-depth what is in here. And and I think I stop here, go for the questions. Yes?
We have 3 questions online.
Okay. Do you have any questions? We can maybe start with questions here.
Thank you,
Yes.
Sylvania, for that quite informative presentation and quite clear. I thought, as one of the applications of diffraction, the aspect of the spatial filtering of the beam.
Yes.
I think probably you can mention that.
Yes. Yeah. Yeah, it's the same thing, because there is this relation between object and the Fourier transform of the object. So if I have a perfect beam, when I do the focusing, in the focal plane, I get a point. If my beam is not perfect, let's say I have a very bad laser, not a uniform uniform illumination, nor a phase constant, I don't get a nice point in the Fourier transform. So when you do the Fourier transform, you get the zero, and you get lots of things around, because they are contributing from these imperfections. Because the point, the nice point comes from the fact that everything was cylindric symmetric, adding in the same way. So if I have a blockade here and I don't have this side of the pupil, or if I have a bad laser, which has a lot of phase disturbance, I can see that the focus field is not going to be good. So what you can do is that when you focus the light, you put a pinhole, and you focus only the center of this, where would be the best focal point. And depending on the size of the pinhole you can choose, you can filter all those garbage that you don't want, because everything that is outside you don't want. And then you propagate again the same F and put a lens again. And then you get back your input beam, but then will be what we say a clean beam, only the Gaussian contribution or like a uniform illumination. So you get rid of all those problems. And that is called Fourier filtering. But you can also use Fourier filtering in the pupil. I will talk about that next time, because you can change the pupil. The pupil doesn't need to be like just a hole. I can make a different pupil, which will make also some implications on what you get after that, in your image, in your point spread function and everything. So you can manipulate both the pupil and or the Fourier transform by adding masks at the Fourier plane. Yes.
First question is, my question basically, so how, okay.
My question is how through geometrical optics of diffraction they can obtain image pattern, for example, airy pattern. Airy pattern you only achieve if you have a uniform illumination, so a plane wave with a constant intensity, constant phase at the lens. And then if you propagate that to the focal plane, you get your airy pattern. That's the best way to get a perfect airy pattern. And the other one, I want to know if they get access to the airy pattern properties to their process, whether in the Fourier transform analytical or experimentally. The airy pattern is a intensity pattern, so it's a modulus square of the field. And when you do the Fourier transform, you get only the field, which is complex. So in order to compare the Fourier transform you make theoretically with the airy pattern you measure, you have to do the modulus square of the Fourier transform of the aperture. And the last, for example, we know that airy beams have some properties as diffraction resistance. Wanted to know how they appreciate this kind of property to their analysis. Well, it's the same way. Instead of being you put a constant illumination in your lens, you can put an airy beam. Airy beam means that it has some intensity and amplitude and phase distribution, and you can look at the Fourier transform of that. And then you see that you get some special properties. But you can use the same theory to calculate what happens to the airy beams, yes. Because that's your pupil function in this case. Yes. There's a question there too, okay?
Thank you. Just probably you can enlighten the participants. A situation where now, instead of passing the beam through a pinhole, now the beam encounters a small dust particle.
Yes.
Yeah. So.
Yeah, you get a different diffraction pattern, and the diffraction pattern can give you information about the dust particle. Actually, that's my work.
Yeah.
I can show next time if you want.
Yeah, and of course, sometimes even if you have a lens and it has some imperfections, it is not uniform in structure. You know, that again can also cause diffraction effect.
Yeah, diffraction is unfortunately very sensitive, so if you have anything blocking the beam, we will see the diffraction pattern, yes. Yes, it's very sensitive. Actually, I use these properties of diffraction and scattering to detect things that are smaller than the wavelength, which is beyond the diffraction limit. Yes.
Thank you. I would like you to bring a clarification, especially on the convolution integral.
Excuse me.
Convolution integral. There is a slide which you had shown convolution integral and OTF.
I don't understand. Sorry. What did you say?
I'm saying there is a convolution integral.
The convolution. Oh,
yeah.
yeah. I didn't go too much in details because you need to look at the properties of Fourier transform. You mean this?
Not that one.
Not that one?
Yeah.
This
convolution
one?
integral and OTF. And also one of the methods in which we can reconstruct an image and also look at the filtering the image is convolution. So I would like to know the correlation. Excuse?
Sorry, that would be this equation here. Let me see. This.
Yeah.
Yeah, because they will have this one. Yeah.
So I would like to get a more clarification on that. And also number two, how does convolution bring a difference in the resolution of an image?
Now, convolution in product is because of Fourier transform. Do you know like that? If you have a product, the Fourier transform is a convolution. But they are related mathematically. So it doesn't matter whether you treat the problem in terms of impulse function, like this one, or you treat in terms of modulation transfer function. They are related to each other because you can also do inverse Fourier transform. So it depends on how you visualize. I like to visualize modulation function, transfer function, because it gives me directly what the details of the image I can get. While here, if I have the point spread function, what can I tell? If I have lots of very complex objects. But when you do the Fourier transform, you spread your information in frequencies, and then you know more what the frequencies contribute to your object. Like, let's think about electronics. Electronics, you have let's say you have a very noisy signal in time, right? Very noisy signal. If you take the Fourier transform, you see maybe peaks. Every peak of a certain frequency. That means that your very noisy signal in time, there is a contribution of a certain frequencies, contribute to that signal. But if you see this noisy signal, I cannot tell where is the problem. But if I take the Fourier transform and I know this is 60 hertz, this is 300 hertz, this is 3 megahertz, I know that these frequencies are causing trouble. And then I can maybe filter these frequencies or do things. So you do the same with the image. So if I take an object, I cannot tell what frequencies are contributed to the object. But if I take the Fourier transform, I know I get a spread of points everywhere, but you know that each point means a certain spatial frequency. For me, I visualize better the Fourier plane than the image, the object plane. You can try that. If you see sharp objects, they have high frequencies. Yeah? So if I have a very sharp square, they have high spatial frequencies. While if I have a very smooth object, they have low spatial frequencies. And then with that, you can visualize. And you can see what's the lens doing, because the lens is going to cut some of those information. And then you know what's going to happen to your object, to the image of the object. Yeah? So making Fourier transform of your object can be very useful. to understand why is your image look like that. Doesn't look very nice, let's say. Yeah? Any other question? There was a question in the back, but I think the person's not there now. You can, okay. No other question? Well, if you have a question, you can talk to me, and don't be shy, I'm here. Yes, sure.
I have a more experimental question, actually.
Mm-hmm.
So you mentioned that to calibrate, let's say, or like to visualize the capability of your system to reproduce the frequencies that are present in your object, in your image, you can use the target.
Yeah.
I think it's the use of target that you were mentioning.
Yeah, it's
the
a resolution target, yeah.
Yeah. And you said that you have to look at the visibility.
Yeah, that's what I do, because you have the 3 bars, and you image the 3 bars, and you make a profile.
So I wanted to, I think it could be interesting to know how to get the visibility information, and
yeah, it's just you make a cross profile, and then you look at the maximum minimum, and then it's maximum minus minimum divided by maximum plus minimum, and then for each grating, and then you see that it goes down.
And you take the edge, or do you fit the edge that you see? I mean, how do you?
Which edge?
So do you, because I guess that you see the edge of the
no visibility, because
just the visibility.
Yeah, that's how we do. Yeah, visibility.
Okay.
Yeah.
The visibility of the 3 bars, not of the edge of 1 bar.
No.
Okay.
No, because what matters is the distance between the bars. Because as they get closer by, you don't see the like as they get smaller pitches, then you don't see going to 0 anymore.
I see.
And when they are outside the band pass of your system, you see just constant. So no, you don't see the grating anymore.
Okay, now I understand. So you measure all of them.
All of them. Make that plot. Make that plot.
Okay.
Yeah.
Okay, I understand. Thank you very much.
Yeah. Okay, thank you.
So thank you, Professor Silvania, for enlightening us on the basics of Fourier objects. So we go straight to our next presenter, Nikolai Kalin. He did his bachelor's and master's at the Nizhny State University in Russia, proceeded to Max Planck Institute for Science of Light in Germany for his PhD. He just defended his thesis on Kerr squeezing in fibers, and he was mentored by Professor Giard. Today, Nikolai will give us a talk on designing multiple fibers for high power fiber amplifiers. Welcome.
Is the microphone? Yeah, good. Okay. So hello, everyone. Yeah, indeed, I'm from the same institute as at least 2 speakers before me, and at least 1 speaker on Friday, tomorrow, I guess. Yeah. So we have quite a number of speakers here, and my talk today would be about multi-core fibers and in general about fiber lasers and amplifiers. I think I don't have too much time today, but because I have also 2 hours on Friday, then we will stop where we'll stop, and we will continue on Friday there, if you take much time. So the outline for my talk is like this. First, we will talk about optical fibers, how they are structured, what it is, what they are used for, and what are the principles of their operation. The next topic would be the modes of the fiber. That would be important to understand on how the fibers differentiate between each other. Then we'll talk a bit about the fiber lasers, why are they important for applications. Then this is more about the theory, these parts, and also we'll talk about some spatial nonlinear effects that are important for high power fiber laser operations and fiber amplifiers. And the last 2 points about the multi-core fibers would be more about the experiments that we did during my bachelor's and master's studies, which are really interesting applications of fibers in terms of going into high power systems. And that also is true for coherent combining. Okay, so we start with fibers, and the fundamental principle for operation of optical fibers is the total internal reflections. So you probably know the Snell's law for the refraction of light on the interface of two media. If we have one media such as water, for example, here, and another media such as air on the top, then if you have a laser pointer, or if you just look directly above, directly perpendicular to the boundary of this medium, then your laser pointer light would just go through, or you will just see the sky. But if you start to deflect your light towards the horizontal direction, then your laser pointer, or again your sight, would deflect even more when it goes out of the water. This is because of the Snell's law of the refraction, and the fraction of the sines of these two angles, the angle of incidence and the refracted angle, should be equal to the fraction of the refraction indices of the media. And then if you increase the angle even more at some point, if you solve this equation for the sine of the refraction angle, you would get some value larger than 1. And that, of course, could not be, because the sines are limited between -1 and 1, or in this case, between 0 and 1. And that would mean that the light could not go out of the medium with higher refractive index, such as water. And the light can only go backwards, and that means, or it can only reflect of the interface, and that would denote the total internal reflection. So this is a very important effect in many fields of optics, and you can see here at the bottom a photo of light going at some angle into a glass piece, and then there is a flat surface, and none of the light goes through, it all gets reflected. So, I mean, it's not only a theoretical principle, but also quite common in our life. So, yeah, in a sense, you can say that total internal reflection captures light in the medium with higher refraction index, and that is very important for optical fibers. So, there are some simple optical fibers which have existed since quite long ago. That is, if you take glass, so silica glass, for example, has a refraction index of around 1.5, and you make a thin rod out of this glass. It can be as thin as a millimeter or even smaller. Then if you launch somehow the light into this rod, then it will follow this, this thin rod of glass anywhere you will point it. And this was noted very long ago, and this type of simple fibers without any structures are used in a number of applications, such as these very nice lamps, where a number of thin glass rods stick out of the some lamp, and that create this very nice effect. Or even in some applications, such as transmitting audio signals via not copper cables, but rather via a glass cable like this. So this technology, Toslink, has been used since, I don't know, 80s, I guess. And this is all possible because thin fibers of glass are very flexible, and you can direct it anywhere you want. However, this is not the optical fibers that are used for telecommunication nowadays. And why is that? Well, because it turns out that when the light is guided within a glass surrounded by air, then whenever anything touches the fiber, somehow the light disappears, gets lost, and so on. So what is currently used as optical fibers is a structure like this on the right here, where you have a few layers. The first two of them, the 1 and 2, are made of glass, and they are called the core, the thin core, and the cladding, and they only differ in the refraction index by some very small numbers. So, for example, this central core can have the refraction index of 5,000ths greater than the one on the cladding. And the light is now guided inside this thin core, which can be as thin as a few micrometers or as thick as 100 micrometers, but still much less than a few millimeters that we considered before. And then this cladding is usually a fraction of a millimeter thick. And its refraction index, again, is around 1.5 because it's made of glass, but a few thousandths smaller than the central piece. And next, because these central pieces are very thin, less than a millimeter in the diameter, then also some buffer and jacket, usually made of rubber, are applied on the top so that the fiber, you cannot break the fiber that easily. Okay. So yeah, modern fibers like this are quite cheap. They're they're used for internet everywhere. It's very easy to produce them. You can lay it around however you want. It has very low losses, around, so now it's even less than 0.2 dB per kilometer. So it's a very useful media for transmitting the light. And if you want to see how they look like in the lab, you can see a picture like this. I'm not sure, probably it's very difficult to see on the slide here, but these thin lines, this one, and also somewhere here, are all fibers with a width of this less than a millimeter. So it's really like fine structure, however, very, very useful for us. There are several types of fibers that are used for communications, and they mostly differ by the size of the core. So the most inner structure can be as thick as hundreds of micrometers or as thin as few micrometers, like 5 or 10. And the ones that have larger core, like here, so in these pictures on the left, the yellowish central part is the core, and this is like the transversal profile of the fiber, and the blue one is the cladding. So if it looks like this, so that the central core is 100 to a few hundred micrometers thick, then this is called a multimode fiber. And with thicker cores, you can assume that the light travels through the fiber almost following the geometrical optics rules. So like this, if you have now this direction is along the fiber, and if you launch a ray of light, it would bounce because of the total internal reflection of the walls and exit on the other end of the fiber. However, if you now decrease the central core of the fiber to smaller and smaller values like this, so that it becomes only a few wavelengths thick, you cannot use geometrical optics anymore. And you have to really solve the equations for the wave optics. And as we will see later, you can make the fiber core so thin so that the fields can only take a specific shape inside of the fiber, and only this specific shape, called a mode, can be transferred through the fiber. So whatever And this is very, very helpful in applications because when you have like a multimode fiber like this, then the signal that you launch, because of the different like optical paths here, can take different time to get to the other end of the fiber. However, with a single mode, whatever in the first order, whatever pulse you launch in the fiber, it will be the same shape of the pulse that goes out of the fiber. So to see the difference between the fiber modes, I will actually I will skip the math behind them, but you have to solve the Helmholtz equation for the transverse structure of the electric field in the fiber, which will give you these boundary value equations. And if you now plot the solutions for that, then the first few modes that you can get that go through the fiber would look like this. This is the fundamental mode that just looks very similar to the Gaussian mode, and it creates a very nice beam that goes out of the fiber. And then the next modes would have more and more zeros in the profile. And then it's easy to see that if you have a multimode fiber that supports more than one mode, then the intensity pattern at the output of the fiber can be quite complicated because you will have a sum of several modes. However, if you design a fiber that only supports the fundamental mode, then this is basically the intensity at the output of the fiber. And it looks almost like a Gaussian mode. You can easily transfer it in free space after that, and it's very convenient for applications. Yeah, the important parameter for fibers, how to distinguish the multimode fibers and the single mode fibers, would be the V parameter, which is shown right here. It basically depends on the core radius A and on the difference of the refractive indices in the core and the cladding. So if the difference in the refractive indices is small and the core is small, then the V parameter is small. And when it's below this critical value of around 2.4, then the fiber only supports a single mode. Okay. For example, here, if we have a 1.5 micrometer light, which is used for internet communications nowadays, and a typical value for fibers, the difference between the refractive index in the core and in the cladding is 5 thousandths, and each of them is around 1.5 for fused silica. Then actually the core radius has to be less than around 4.8 micrometers, as shown here, for this fiber to support only a single mode at this wavelength. So this is actually true for the fibers we use for internet nowadays, for the standard fibers. And these fibers are now so important that in 2009, this Sir Charles Cowell-Quinn has received the Nobel Prize, or part of the Nobel Prize in physics, for his efforts to create these low loss and very practical optical fibers, which before him was considered to be impossible to create. Yeah, then what we have to do now is to go and consider how we can use these fibers. Oh, it doesn't work. No? Yeah, it works. Okay, so as you've heard yesterday, or maybe even before, to make a laser, you have to prepare these three parts: the gain medium, where the signal would be amplified, where your optical signal would gain power; then the resonator, or in other terms, the cavity, the feedback, the optical feedback, so that your amplified signal can go through the medium, through the gain medium, again and again. You can do that with mirrors if you build a free space laser, for example. and a pump that will pump your medium to bring the energy to the laser. And it turns out that in optical fibers, it's rather easy to implement all of these three elements. So since the fiber you can bend however you want, you can simply loop it so that when the light goes in one direction, it will return after some time to the same fiber, and therefore you create the resonator. So you don't need actually any mirrors, you don't need any structural components. You can create a loop of the fiber, and your light will return to the same place over and over again. So that is very convenient and easy. To create the gain medium, the silica in the fiber core can be doped with some usually rare earth elements such as erbium or ytterbium to provide lasing or to provide gain at different frequencies. Telecommunications nowadays, and for example, ytterbium is used for wavelengths around 1 micrometer, and that is nowadays used for powerful lasers, as we will see later. And the remaining part of any laser would be a pump, and pumping can be done with laser diodes, which are nowadays have like direct output to a fiber. You can directly couple it to the ring cavities that you have for your laser. So in a picture here, the simplest fiber laser is shown, where with number 1 we have the active fiber, so that is the fiber doped with active ions. Then the light goes through this active fiber. Then there is some polarization control that you need for the fibers, but that's not very important for us. And also an isolator to make sure that the light only goes in one direction, but not in the other direction. And then you have these very standard optical components for fibers, the coupler, where the light, so the coupler has 4 ends. 2 of them are connected into this cavity. One of them is used to bring in the pump into this active fiber. So the pump connects to this end, which is also an optical fiber. And after the light goes like this cycle, it can exit this way. So the coupler just creates some coupling between these 2 fibers and these 2 fibers. So the fiber gets, the light gets more power here and then exits this way. Or as an alternative to a ring resonator, you can also make a normal resonator, like with a standard laser scheme when you have an active medium and then you have 2 mirrors at the sides. You can also do that in fibers. I'm not sure if you can easily see that here, but if you have like a doped fiber, so the active medium in the middle, and you create a fiber grating at each side of this doped fiber, then your light you can design the fiber gratings in such a way so that the light gets reflected, or most of it gets reflected at both ends, and therefore you have a resonator. Then you can just launch the pump on one end and get the output of the fiber at the other end. So again, there are basically no elements or no difficult elements in this laser design, and such fibers are very robust, and there are some additional benefits of these lasers. So they are usually simple and robust. They provide good beam quality. If you have a single mode fiber, then your beam at the output would look very similar to a Gaussian mode, and you can use it everywhere where you want. There are also some not very obvious benefits of fiber lasers in comparison with other types, such as high pumping efficiency, because again, for example, in a ring resonator, your pump would also, the not absorbed pump would return to the same place, to the same active fiber again, and can be absorbed again. so it is not lost. It is quite easy to cool down the fiber lasers because you have just a thin piece of fiber. You can do whatever cooling that you want on this. You don't have like a bulk crystal which is heated somewhere in the middle. And of course, there is this advantage that you can extend the fiber laser, attach it to some fiber, and bring the beam, so the radiation wherever you want, in the next lab, in the next building, or on the other part of the city if you really want to. On the right here, you see an actual photo of a fiber laser from the lab. So this is just some shelf with a few elements on this shelf lying around, and the green that you see on the slide is some fluorescence from the active fiber when it's pumped with laser diode. Some of the light escapes as a green light out of this fiber. There is one problem with the fiber lasers, though, is that typically you can only afford so much peak power, much less in comparison with bulk lasers, for example, because for the whole length of your laser, your beam is confined in these few micrometers of the fiber, and therefore, if you have large power, you have also very high intensity, and high intensity breaks elements. So this is what we actually want to avoid now, and we will see how to avoid this, why it is important to have low peak power in the fiber, and how to actually create some high power fiber lasers. But before we go there, I want to show a couple of pictures here. So yeah, nowadays the fiber, this is a picture that I already saw on the previous slide. This is the simplicity of a fiber laser. This is the same thing, but now it's viewed through an IR viewer, because most of the, or maybe even all the fiber lasers are in infrared wavelengths, so you cannot see the radiation with your naked eye. You have to use some special devices like infrared viewers that converts the infrared radiation to visible light. And then if you look at the fiber, so what you actually see here is an active fiber. Some of the radiation still escapes this fiber, and you can see this on the IR viewer, the process of amplification here. And on the left here, you have different systems, different industrial systems which create really powerful fiber lasers, from the small ones to really, like, well, sometimes they get bigger when you really have to have high power. So if we really want to go to high powers, then in fibers you always in lasers you always have two different regimes. Either it's a continuous wave regime, so that the radiation is constant, and usually you want to create that like a single mode, a constant sinusoidal beat, or you go to pulsed lasers where your pulses only appear once in a certain time, but these pulses have very high maximum intensity. So for the same average power, if you average over time, then the CV lasers, like constant wave lasers, would have very low peak intensity, while the pulsed lasers would have very high intensity. And that is, again, very beneficial for some amplifications, both in like industry, where you don't want to heat the object you shine your laser to, like metal, for example, but you want to destroy it, so the the pulsed lasers are used now in medicine or in industrial, like metal cutting and metal welding and so on. And as we know, the fiber lasers cannot have high peak power because of some nonlinear effects that we will also consider. But for the average powers are pretty good, and actually one of the most powerful CV lasers are fiber lasers, which can reach the average power of like 10 or even hundreds of kilowatts. So this is really, and this is like a constant power, so you get this 100 watt every second, kilowatt every second. And this is usually done on the setup like here. Again, it's maybe the text is too small, where you have some seed laser which generates this very nice CV light with very easily tunable properties and very controllable environment. But usually it's difficult to create a laser that just outside of the resonator would create a high power beam. So this laser has to go through some amplification stages, as shown here, amplification and amplification, to get high power. At the output, this is a typical scheme that is known as a master oscillator here and power amplifiers here, and then you can get high power. And this is fine if you do the constant wave lasing. If you want to do the pulsed lasing, then probably you want to use some techniques that are also known for other types of lasers and about which you have heard yesterday. For example, the chirped pulse amplification here, where you first would stretch your signal so that the peak power gets lower. Then you would amplify this stretched pulse without getting over the limit for the peak power again. And then you would compress the pulse again, but now, because this is a fiber laser, this compression has to be done outside of the fiber, because otherwise the fiber would break. And then the scheme would be again this up here, and there are two additional elements, the stretcher and the compressor, which respectively do the stretching and the compression of the pulse. And the stretching can be done in optical fibers, and it was actually the first experiment for which the Nobel Prize was given, used this fiber stretcher to do the stretching in the CPA, but then the compressor has to be done somewhere else. And yeah, this is some progress of CV fiber lasers, of their power, and this is a little bit outdated. I think it's 2015 here, where they already reach around more than 10 kilowatt of constant wave power. So, I said a couple of times that the peak power should be limited in fiber lasers, and but we have to consider why and how is it limited. So we know from other talks as well that when the intensity gets high, the elements of optical systems can get damaged. But this is for intensity, and in principle you can make fibers with larger cores and larger cladding, so that the intensity, that is the power divided by the area of the mode, is not that high. However, there are some nonlinear effects that actually limit the total power of the pulse. I mean the total peak power in the pulse, but not the intensity in any point of the fiber. And the effect that limits that is connected with the Kerr effect that you've already again heard about yesterday. So that is, the Kerr effect is the third order nonlinearity in the polarization induced by the electric field. So you know that when the light goes, or the electromagnetic wave in general goes through a medium, then the polarization induced in this medium depends on the electric field. And then normally in a linear medium you have only this first term, so that the polarization is proportional to the electric field. However, in principle you have many terms, and the Kerr effect would be the third order term here. Why the third term is important and not the second one? Because the second one is usually higher. That is because in isotropic media, such as glasses, for example, because they are amorphous and isotropic, the second order polarization cannot exist because of the symmetry. So this term is exactly 0, and therefore the lowest order nonlinearity that you can have in the fibers, well, at least those made of glasses, is the third order nonlinearity here. So the polarization depends on the third order on the electric field, and if you do the math, you could also see that basically this is transformed to a change in the refraction index n. So the refraction index n now begins to depend on the square root, on the square of electric field, that is the intensity of your pulse. And then Kerr effect leads to a number of effects in optics. Some of them you have already heard about yesterday, such as Kerr lensing to synchronize the modes in the laser. But it can also lead to some bad effects, for example, in fiber lasers. And we will consider one of them. This is the self-focusing. Again, this is the same effect that you heard yesterday about when you considered the Kerr lens helping to synchronize the modes in the laser. But now on a much smaller scale in the fiber, we know that due to the Kerr effect, the refraction index in the center of the pulse is increased, and therefore it creates like a lens inside of the fiber. And we know that this lens focuses the light even more, so that it can create an even bigger lens. And the only effect that limits this creation of the lens is a natural diffraction inside of the fiber. So in this glass medium, the light would normally diverge, but then because it creates this additional lens due to nonlinearity, the divergence is not that big. Well, in fibers, the divergence is limited by the shape of the fiber, by the total internal reflection again. But even in this case, if the nonlinearity is so high that this lens is higher than the divergence, then the pulse would collapse even inside a single mode fiber. And that would raise the intensity in the center of the pulse by orders of magnitude, and the fiber would be damaged. And the issue with that is that you cannot overcome this problem using larger fibers, using fibers with larger mode area where the peak intensity is low, because this effect has a threshold not in the intensity but rather in the total power of the pulse. And if the total power is above a certain limit, which is of the order of megawatts for silica fiber, then eventually if you have a long enough fiber, and fibers are typically long, your pulse would collapse and you would damage the fiber. And as an example here, there are some, well, not very typical, but quite reachable parameters of a fiber lasers with a 400 femtosecond long pulse and the average power of 400 milliwatts. With the repetition rate of half a megahertz, you would already reach a peak power of almost 2 megawatts. And these are the parameters that is not very hard to reach in a lab. So we are now really close to this limit of self-focusing, and this is one of the effects that limits the further increase in the peak power of the lasers. So some of the possible solutions to this would be either coherent combining, where you get a few sources of radiation and then somehow you add them up so that the pulse that you get at the output would be the sum of all the pulses of all the power that you have in several fibers, for example. Or another solution would be to make special fibers like the multicore fibers that I will show, in which this effect of self-focusing is not is mitigated by some means. So yeah, I would like to go to the multi-core fibers, but I think I also see that it's time for lunch. Is it better for me to break here, I guess? So yeah, I think I will continue then on Friday. And if you have any questions, I'm happy to answer them.
Thank you for that insightful presentation. But I just have a question. Your presentation has been on fibers, right? Fiber lasers.
Yeah, fiber.
But I have an unrelated but also related question.
Yeah.
When you want to make an application, say you want to design a basic communication system, and you want to use pixel fiber transceiver pair. You've heard of pixel, right? The vertical cavity surface emitting laser.
Not really.
Okay,
So I'm not really a communication person in fibers yet. So if you have a question about the fiber communication, I think you have a lecture somewhere on the next week.
Okay.
So I'm more about lasing and amplification in fibers.
Thank you for the nice presentation. Very informative. You mentioned that only in infrared. Do you know if it's possible to go a little down in the near infrared?
I mean, so the typical fiber lasers are around between 1 and 2 micrometers, so it's near infrared already. Whether it's possible to go to the visible, I don't know any direct, like fiber lasers that directly generate visible light. However, I know that it's possible to go to that using near infrared generation and then some nonlinear effects like, well, we cannot have second harmonics inside of the fiber, but we have the Kerr nonlinearity, and basically this can generate a supercontinuum which can also reach the visible region. Or you can, of course, stop at the exit the fiber and then have a second harmonic generation and something like that.
Thank you.
My question goes to when you mentioned that we can have lasers which are built based on fibers. I believe that it gives a limitation in the sense that, as you mentioned, majority of the fiber optics cables are made from centrosymmetric materials.
Yes.
And that means, therefore, that second harmonic generation cannot happen.
Yes.
And also, for example, some frequency generation or difference frequency generation will not happen, and therefore you are limited in terms of generation of other beams.
Yes, 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 indeed. This is one of the limitations in the fibers, because they're made of isotropic material. We don't have a second order nonlinearity there, and therefore all of these effects that you mentioned are not possible inside of the fiber. And well, in principle, I've heard about some ideas to incorporate some crystals or to make fibers out of crystals, but as far as I know, they either have high losses now or not very practical for now. But you can, whenever you want to go to have some second order nonlinearity, you can just leave the fiber and do all the things that you can do in the bulk optics. So you can install a crystal and so on. And given the fiber lasers, you would have the advantage that your beam is very nice, looks like a Gaussian beam, and you can focus it very tightly in the crystal and so on. So I would consider this as an advantage rather, but of course, this maybe removes the advantage of being very robust setup, because you have to align the elements there.
Some more questions?
Thank you, and I will continue about this on Friday.
So thank you very much, Nicolette, for the presentation. I think now we break for lunch. Am I right, Mobile? After lunch, I'll give you the mic so that you can give us directions.
Now we will break for lunch. Then in the afternoon, we will go for the poster session. It will be behind this building. Then we interact with the speakers. You have a question, you can ask during the poster session. So feel free to interact with the speakers. Feel free to interact with the participants during the poster session. Thank you.
And it's formed in three. We have three parts of this. We have the Schack-Hartmann wavefront sensor. We have the deformable mirror and the control software for this purpose, and that makes the first type of this.
Whatever is before you is Michelson interferometer, and one of the applications of Michelson interferometer is that it measures the thermal expansion coefficient.